Good morning, sir.
Good morning.
How are you, sir?
मैं कैसा होना चाहिए?
अच्छे होने चाहिए, sir.
मैं कुछ सही हूँ?
Start करें, sir?
हाँ बिल्कुल सर.
Okay. Very good morning to all. On the behalf of Department of Computer Science and Engineering, I, Dr. Kumar Pal, welcome all the participants on the fourth day of our STC formal verification. It is a great pleasure for me to introduce the speaker of this session, Dr. Mahesh Chand Govil. Dr. Mahesh Chand Govil is currently the esteemed director of NIT Sikkim and a professor in the Department of Computer Science and Engineering, MNIT Jaipur. He received his PhD in Computer Science and Engineering from IIT Roorkee. He has more than 30 years of teaching and research experience. He also has a vast experience as an administrator. Some of his administrative responsibilities are founder HOD of CSC Department, MNIT Jaipur, founder principal of Government Banswara Engineering College, Dean Faculty of MCA RTU Kota, State Project Coordinator SPFU Cell, Government of Rajasthan, Director on the Board of Rajasthan Knowledge Corporation Limited, Coordinator of IIIT Kota, Director Center of E-Governance Jaipur, and currently sir is serving as a Director NIT Sikkim. His research interests include real-time system, parallel and distributed system, fault tolerance, and cloud computing. He has completed many research projects and consultancy. He has more than 100 research publications in reputed international and national journals and conferences. He has guided more than 10 PhD scholars and many master students, and is currently guided few more students in research area like RTS, cloud computing, computer networks, and more. He is a member of IEEE and has a lifetime membership of ISTE and IETE. Now I request Professor Mahesh Chand Govil, sir, to kindly join us for a great session. Thank you. Over to you, sir.
Okay, fine.
Sir.
यहाँ से आवाज जाएगी पास में?
नहीं जाएगी बाबू वहाँ से. हाँ PDF है ये.
Okay, so good morning to all of you.
Good morning, sir.
First of all, I would like to give thanks to NIT Jalandhar, especially my friend Dr. Lalit Avasthi, the director of NIT Jalandhar, and the coordinator of this STP, Dr. Kumar Pal. Right? And I think this is a very apt topic because at times we feel when we study the subjects related to this, just like your automata theory, and we at times think, okay, why this subject has been taught and why we are studying such kind of a very boring subject, because a lot of mathematics is there and a lot of formal aspects of the subjects are there. But I'm thankful to the Kumar because he has given me a chance to go through this topic, and I realized that at times this computational theory or your automata theory is a very, very important in the modern world, because this is something which is required to design and implement the most of the systems, right? So we'll begin with this, my formal talk on the formal verification. So this talk is more towards the real-time system, because now the use of the real-time system day by day is increasing and becoming more important. Now, as this topic says, this formal verification for cyber physical systems. So now we all understand what the cyber physical system is. We are talking about the IoT, Internet of Things. We are talking about everything through internet, and so many buzzwords are being used in the computer science domain. Now we have to really ponder, right, what is a real-time system is, and whether these cyber physical systems You can name the large number of cyber physical system, or rather we are heading towards converting all physical system into the cyber physical system. That is a dream. And I understand that everybody knows about the cyber physical system because they should have a capability of controlled through an intelligent device, or they should themselves should be intelligent enough to take decisions and control and provide services to the human. That is the prime requirement of all cyber physical systems. But talking about the cyber physical system is very simple, but when we design the cyber physical system, there are large aspects of designing. And it becomes at times very difficult to provide the reliable cyber physical systems. So the question comes how we can construct or can build a reliable cyber physical system. When you talk about the reliability, we'll ponder more on the reliability. The reliability is not a small word. This is a big word for the computer science community. So let's first understand what the real-time systems are and why we say the real-time systems designing is very, very difficult as compared to your normal systems. Now we define the real-time systems. Real-time system may be defined as one whose principal measure of performance is whether or not it meets pre-specified task timing constraints or deadlines. So basically the emphasis on the timing constraints. Generally these timing constraints can have a varied granularity. The time constraints may be very rigid, may be very large, but here we mean where the time granularity is very, very small, because if I consider you can consider when you are typing on a word can be a real-time system because it doesn't give you a reference in a given time, then you sometimes feel irritated. So in sense, you can say my word is also a real-time system, but that's not the meaning of the real-time system here. The real-time system here we mean which deals with the more critical applications and the control time available to is very, very small. And the decision has to be taken within that time. So that becomes very important. Therefore, it can be defined in another way also. The term real-time system can be used to describe any information processing activity or system which has to respond to externally generated input stimuli within a finite and specifiable delay. Now, what this specifiable delay is? So generally, we term them as a deadline. We'll discuss a little more. Now, any system can be divided into two major components. One is the control system, and another is the controlling system. Generally, controlling system can be your small microprocessor, can be a small electronic circuit, right, which controls the underlying environment, or it can be a supercomputer. So it depends what kind of the activity we have, or what kind of the system we have, and depending upon that, the size of the control system as well as the control system can vary. So this is a typical diagram, right, which shows you some components of any system. So controlling system is basically having monitoring system, and then it has to issue some sort of a command and control. Then we have to take some actions, so you need actuators, and sensors are being required to give you the feedback from the health of your controlled system. So sensors are a very important part of any automation system. So we are talking about the automation. So of course, the two integral components are sensor and actuators are equally important. Both the components can be hard also, can be soft, right? So depending on the system, we have a soft components as well as the physically hard components. Now, real-time task, we say generally each and every activity in a computer science is being termed as a task, right? We are well familiar with the job, or we are well familiar with the name of the process, but we understand, right, there is a difference between a task and job or a process. So runtime activity, generally we term them as a job and task, job or process, but task is a general terminology which is being used. Right? Interchangeably in the computer science domain, we use the word task for job or process at times. So distinction between these three words is not there when we go through the literature. So it depends on the instance, or it depends upon the sentence which is being written to give us an idea whether the mean of the job, task, or the process. Now we have to classify it, because generally when we talk about the non-real-time system, the classification of task is not there. The task, right, is there. Generally we need, okay, now we have some activity to be performed, but we are not going to divide the activity very precisely into the different categories. But when we deal in the real-time systems, because your process or the algorithm which you design to do the task differs or varies depending upon the nature of the task. Therefore, the classification, understanding the classification is very, very important. Now, activity criteria for division of the task is periodic, aperiodic, and asporadic tasks. So, periodic tasks are generally the tasks which repeat themselves over the time after a given period. So, therefore, the name period is given. And these are very, very important as far as the real time is concerned, because they normally the tasks which are responsible for the supervision of the system. When we say the supervision, they generally provide a feedback path, and they are also responsible for the stability of the system. So the periodic task becomes very, very important. The aperiodic tasks are the tasks which can come at any moment, and generally we say they arrive at a random moment, and you cannot predict their arrival pattern, or you cannot predict their arrival time. So aperiodic tasks, therefore the term aperiodic task is being used. Now there are certain requirements of the real-time system which we'll discuss, and therefore the third category is for the asporadic tasks, because the aperiodic tasks which are critical in nature has to be satisfied as far as their deadline is concerned, and therefore the methods which are available for providing a guarantee to aperiodic tasks are not very you can say the correct. Therefore, we convert our aperiodic task into the periodic task, and therefore the aperiodic task which behaves like a periodic task are termed as a asporadic task. And the difference between the periodic task and asporadic task is the periodic tasks are defined by its period. Okay, this is a truly a equal interval. We divide at equal interval. The asporadic tasks are being defined by interval time. And interval time can be fixed, can we say, okay, now we have to follow some maximum value or some minimum value, right? But asporadic task is, you can say, is being the combination of periodic plus the aperiodic task. Second criteria is also very important, because as we have said, all the tasks are marked with hard, firm, or soft. So hard, where you cannot afford to lose the deadline. The firm is right, the results which you deliver to the system after the expiry of the deadline are not useful. So usefulness of the result expires with the expiry of the deadline, and therefore we term them as firm deadline or firm deadline systems. The third one is a soft, where you can afford to lose some of the deadlines depending upon the nature of the activity, just like online video conferencing or the online delivery of, let's say, this lecture is there. Even if you miss some frames of delivery or some frames or some packets of the voice, you can understand what the opposite party is speaking, and therefore that is a soft. Okay? So they do not have a very stringent timing constraints or place of the tasks. Now, the important requirement of the real-time system is the speed is, of course, is necessary, but we say it's not sufficient, because your speed cannot guarantee the meeting of the deadline. The predictability is something which is very, very important, and is an essential characteristic which has to be met for the real-time systems. Reliability, of course, and the adaptability. Now, how we define the predictability? The predictability is defined as the ability of the controlling system to determine a task's completion time with certainty. So this word certainty is very, very important. In ensuring that all hard deadlines will be met, taking system state and task resource need into account. So this is something like you have to do a bhavishwani in advance. Okay, I am going to satisfy all my timing constraints, And if you miss a single instance of your timing constraint, in case of the hardware real-time system, the result can be catastrophic. And we say when it is catastrophic, it can result in a loss of life, or might be the financial loss may be very huge. Sometimes we give the example of the Bhopal gas plant, right? The failure of controlling system, right? Or your sensing environment has resulted in a death of the large number of people over there. So these are some examples where you are have to be very, very particular at the time of the designing. Okay, now my system design is something which satisfy the requirement of the predictability. Of course, this is not an easy characteristics of the system which can be satisfied. And here probably we need all the formal methods apart from the other techniques to verify the properties as well as the requirements of the system that they will not fail under any circumstances. So there is one example, right? You say there is you designed a air defense system for monitoring the skies or enemy tasks. So you can understand the nature of the stars. If you miss the target, what can be the consequences, right? So you may not be your aircraft as well as the pilot cannot be right there. If you miss the deadline to hit the enemy aircraft, right? So we can understand the need of the predictability of the system design and right put into the aircraft defense system. Now, generally, because we have a varied right requirement and varied nature or the hybrid nature of the systems which are available across the world, and therefore you cannot talk about the guarantee, right? So generally we talk about the two type of the guarantee: the static guarantee, which you can give at the design time. When you are designing the system, there itself you can ensure these activities can be guaranteed as far as the timing. We are concerned on the timing constraints here, right? Other kind of the characteristics can be met easily, but the timing constraints are very, very difficult. So at times, the static guarantee is the guarantee which has to be given at the time of the design. But there are some activities, as in the previous example we have discussed, which is truly a periodic task, right? And the static guarantee is not possible because we are not knowing the task characteristics in advance. So we have to resort to the dynamic guarantee methods. And designing the procedures or algorithm for dynamic guarantee becomes very, very difficult, because at times you do not have time to run even your algorithm, right? And therefore, the dynamism of the system is very difficult to handle in real-time scenarios. Now, reliability is important. Everybody know what we mean by the reliability. But here, the reliability is in a different sense is very, very important. We always talk about the reliability of the hardware. The hardware should not fail, right? And therefore, we talk about the redundancy, right? You can have a redundant component in the system. So one component fails, and then the another will take care, and then the system will continue to function. For example, in the aircraft, we generally have two engines, while in car you have one engine. Because if your car fails, fine, nothing is going to happen. At the most, your time is being wasted, or right, you may have to work for a longer distance, right, and so many things. But if it is in the aircraft, right, if something goes wrong in the engine, then you can know what can be the consequences. Therefore, the hardware reliability as well as the software reliability can be handled by redundancy. So generally, when we talk about the critical applications, we have redundant part in terms of the physical parts as well as software parts. So we talk generally both hardware reliability as well as software reliability. But when it comes to the real-time systems, the reliability in time is also on need. And therefore we talk about the temporal correctness or the temporal reliability. So your system should provide you guarantee against the delivery of result within the time limits which you have specified over a given task or the application. So therefore, the three kind of the reliability we have to talk in the real-time system. One is hardware reliability, second software reliability, and third one is the time reliability or temporal reliability. Adaptability is of course is a general requirement for any system. We to adapt, right? God has designed us, right? So we are the perfect example of the adaptive system. So adaptive system, why we need an adaptive system that is there, right? So it reduces the cost of the refinement, the computing of the resource, and so many things. So adaptability is something which is another very, very important and desirable characteristics. But at times the adaptability, if we are not able to imbibe, is not an essential or critical requirement. Now there is a difference in the real-time system when you talk about or when you compare with the general purpose system, right? So we say the real-time system, right, paradigm is very different from the general purpose computer systems. In what sense? The dynamics of the underlying physical process placed explicit timing constraint on individual tasks, right? So these timing constraints can be in the form of when your task will start, when your task will finish, what can be the difference between the consecutive tasks, right, where the one executes. So we can talk about a little bit of dependency in terms of the time within the task. So we say the time is the most precious resource in the real-time system. So you have to manage your time, right, correctly. So correct management of time becomes very, very essential. Another important thing with the real-time systems is they are placed in a hostile environment. Because generally, general purpose system computers are placed in a very well-maintained environment with AC and everything. But when you talk about the real-time system, this might be a tiny real-time system which may be placed in the field where temperature as well as humidity and other, right, are very words. Now, another difference in the case of the real-time system is the performance determination. So for non-real-time system, we say average case performance is important because when you talk about the performance, there is a money involved. Okay? Design at the time of the design, there is a money involved. If I say my performance should always be right, excellent, then I have to put more cost. So many issues comes over here as we have discussed in the past. The reliability, the fault tolerance, and so many things. But for non-linear system, we go for the average case performance, and we have to make a balance in the cost and performance ratio. But when it comes to the real-time system, right, the cost is not a major criteria for design. The reliability is the major criteria for the design, and therefore we do not care for cost performance ratio. We care that my system should not fail under any circumstances, and therefore the design criteria is the worst case scenario. So you have to consider all worst case scenarios of your system when you design a real-time system, right? So there is a common code, right, which says, then there was a man who drowned crossing a stream with an average depth of 6 inches, right? You can understand there is a river where shallow river where the average depth of that river might be 6 inches too less, maybe let's say 4 feet. But right, when you are crossing the river, there might be a well within the this river, and you do not know, right, or you know what can be the consequences if you happen to meet the well. Which is might be let's say 100-meter deep or something like this. So we can understand if this course gives us an idea what kind of the design concepts we have to follow for real-time systems. Now another issue is when you go for the verification or modeling of your system, right? What should be my performance matrices around which I have to capture my requirement or the specification for the system. So your performance matrix provides you a guide, right? What kind of the design criteria I have to go through. Okay, so this is in terms of the scheduling because the most important activity in every system is the scheduling the tasks apart from other things. So they are we talk about some performance metrics which are used in your general purpose computer systems. So some of completion time, the shortage of fast scheduling, FCFS, and right? At times the priority scheduling and so many things. So you have to at times determine the average turnaround time or the average response time, right? So many things. But they are not good for the real-time system because they are not addressing your timing constraints. So timing constraints involve one of the most common timing constraint in real-time system is called the deadline, right? So the performance matrices which are not addressing the timing constraints are not useful for real-time systems, and therefore we need to define different kind of performance matrices, right, for modeling as well as designing, modeling, and the performance determination of any real-time systems. Some of the example is let's say tardiness, lateness, miss rate, loss rate, or the percentage of the deadline met or percentage of the deadline right miss. Right, these are the kind of the performance metrics we have to look for. The problem of scheduling, when we discuss in non-real-time system, we are not concerned about the suitability analysis because you are not concerned about whether your task is going to take 1 hour, 2 hours, 3 hours, 4 hours. You concerned only, okay, now my job should be done maybe 1 second, maybe in 10 seconds, or maybe in 1 hour. And therefore, we are not much concerned. We are concerned only the task should complete and finish, right? Of course, the response time is always important, and we try to finish the time as early as possible. But when the scheduling solutions are to be designed for the real-time systems, the foremost issue is whether the algorithm which you have designed for the scheduling satisfy your timing constraints or not. How would you satisfy the timing constraints? That is the question. Should I go for some sort of a test which let me know the scheduling solution which I have designed is correct as far as the time is concerned, or the scheduling solution which I have designed is reliable for the system under consideration? And to answer this question, we have to perform the feasibility analysis or the suitability analysis. Again, the suitability analysis or the feasibility analysis can be static, can be dynamic, right? So, first step in a scheduling as far as the real-time system is concerned is the suitability analysis. Whatever the technique or whatever the approach you need, you have to analyze through various mechanisms we discuss, and then test whether your solution satisfies the requirement, especially the timing requirement of the system or not. Once you ensure the timing requirements are met, then I can order my task for the execution. Because I have tested or I have guaranteed that my all deadlines or all timing constraints will be met. So suitability analysis is the first and the foremost important step of the scheduling in real-time systems. Now, suitability analysis, as I said, right, is used to predict the temporal behavior of the real-time systems. When you say predict the temporal behavior of the real-time system, we are talking some sort of the techniques which let you know that the temporal behavior is correct before the system is being put to use, right? So your system is not in use, and we do not have a prototype. In advance, we should have some techniques where temporal behavior correctness can be guaranteed, right? And therefore, probably we need to go through these formal verification techniques, or we have to understand or design the formal verification techniques so that this temporal behavior for any system can be predicted in advance, right? With guarantee, prediction with guarantee. Now, in case of the real-time system or any system, the notion of the suitability test, right, is used. So suitability tests are not, but they are the algorithms, okay, or they can be put in terms of the mathematical formulations or some other formulations where you can write, prove their correctness as well as reliability or other, you can say the requirement consistency and so many things. So, you know, there are so many issues which comes into the picture, right? Even then, these process synchronization an issue when you talk about the suitability analysis. So is there any deadlock? That is the question mark. So suitability test does not only consider the temporal behavior, right? Your task might end up in a deadlock, and if there is a deadlock, you can understand, right? If it is a hard real-time system, what can happen? Just imagine you have a nuclear power plant where you are controlling, right, the reactor, okay, and something goes wrong, right? What can be the consequences? Or you are controlling the temperature of a reactor, and every system has some maximum or minimum limit, right, for right its safety. And if those safety limits are being violated, we can understand the fate of the system. So therefore, the suitability test or the you can say the suitability analysis becomes very important. Now we generally go for modeling of the system. So we talk about the simulation and modeling, and we have a subjects in various right classes, right, modeling, simulation, and but at times we do not give more attention because we think, oh now we can why we should study this simulation and modeling techniques. But any system, if you want to design, we need to know how to model the system, what modeling is, right? How to really test the model which I have prepared is correct or will perform well when it is put to use. So there are so many questions. We always say when you model a system, it should be good. How to model the system in a good form, that is another question. So we generally have some sort of a guidelines, right, how to model a given system. So we say generally we should concentrate on the relevant details rather than the irrelevant details, right? So some example given here, like the latest of the process which I am going to use for my system is not important. What is important? The speed might be important. Its right reliability might be important. Okay, so these are the few things which are important rather than this. So we say for real-time system, timing properties is important. What are the resources are required for the system, right? How do I going to allocate those resources and how I am going to control those resources? These details are important. There are some points which also talks about, right, how the modeling techniques or the models should have some sort of a characteristics. Now, what are the important model of any what are the important elements of any model? So for this, workload model is one which describes the application support system by the system. Then resource model, what kind of resources you have and how you are going to, what kind of resource you need when it, right, given task is to be performed by your system. And then the set of algorithm, large set of algorithm is required, right, for how to do the tasks and how to use these resources to perform those tasks. So algorithm is a very important part of your this reference model. So algorithm may consist of your what are the techniques you are using, right, for not only for the activities, but also for, let's say, verification, validation, and so many things. There are some more points on the good reference model, right? There is some, not an exhaustive list of the temporal parameters. This is some sort of, just to give you an idea, this is not the deadline, is not only the temporal constraints or the timing constraints. There might be more constraints or the temporal constraints which the real-time systems has to talk. So we say phase of the periodic task, right? It talks about when your task arrives in the system. And when your task arrives in the system makes a difference in the design of the algorithms or design of the scheduling analysis, suitability analysis. Generally, to simplify our own life, we consider the periodic task comes, all the periodic task comes at the same time, and that is being denoted by 0. So my suitability analysis becomes easier. But if you go to the practical scenarios, right, this is not the case. The periodic task can come at a different time, and then the same technique which I have designed for the suitability analysis may not applicable to the different scenarios. So the phase of the periodic tasks, right, makes my life very difficult when I go for the suitability analysis, right? So The release time of the periodic task is also important. Generally, in the periodic task, we assume that the task characteristics are known in advance, and therefore static suitability analysis technique can be used. But when you come to the periodic task, right, the dynamic suitability analysis techniques are required because you do not know the task characteristics in advance. The task characteristics are known when your task arrives in the system. So release time, absolute deadline, execution time, right, start time, temporal distance is something which talks about the distance within the two tasks, right? So sometimes I give them an example of your movies, right, where you have to play the video as well as the audio. So what should be the maximum distance or maximum time difference between the audio is played and the video is played? In the old movies, when it becomes very, very old, you might have seen your audio is not synchronized with the lip movement of the actor. What was the reason? Because your video and audios are two different entities played differently. And when the synchronization between the video and audio is being lost, right? So we can find that lip movement are different from the audio. So they are the applications where you have to define the maximum start or maximum finish time between the two given tasks. So temporal distance is a distance between these two kind of the tasks. And therefore, the algorithm which have to be designed for such applications, even the verification techniques designed for such applications, are to be different than the other. Period I have already said, right? This is the difference in the arrival time of the two consecutive periodic tasks. Release time jitter is also very, very important in real-time systems because you talk about the satisfiability of deadlines. If there is a difference in the time which you have defined at the design time and at the execution time, then your suitability analysis will not be applicable at runtime. So therefore, when we design the suitability analysis at times, we have to take this release time data into the consideration, and then we do the analysis of the algorithms which we use for the suitability or the suitability analysis. So therefore, the release time jitter is very, very important in real-time systems, which is not important in case of your non-real-time system. Let's take an example of your, again, the fighter plane, where you have to shot the missile, and there is some time gap when you have issued a command and your processor really releases the missile. And even a small fraction of time makes the missile to miss its target, right? So becomes very, very important for time critical applications. So there are many examples you can give for that. Relative deadline of course, right? Depends how you are going to implement. Interrupt time, I've already said, this is the time between the two consecutive instances of the given task. Finish time, of course, is everybody knows. The hyperperiod is something which we define in the real-time systems, right? So this is the LCM of all the periods of the periodic task. And this term is being used when we do the suitability analysis, right? So we're not going into the much detail here. Now we'll come to the formal verification. Right? So with this, I think you might have understood, right, why the correctness of the real-time systems as far as the time is concerned is very, very important. Now, what are the techniques which we can use to ascertain the correctness or the timing constraints or the timing correctness of these systems, especially real-time systems? Because as I said, when you talk about the cyber physical systems, even the gas stove in your house is a critical physical system. Because if you think a little, your gas stove might have a critical application, just like if you remotely switched on a gas and you put something on the gas and let's say your system fails. or it does not behave in a timely manner, what can be the consequences, right? Similarly, many applications, right? We generally talk about this smart home. So in a smart home, there are air conditioners, there are so many things, right, which has to be controlled remotely through your mobile or through maybe some remote device. And there they have a large number of real-time applications. So we can't say any system can be purely a real-time systems. Every system is hybrid in nature. It has some real-time requirement as well as non-real-time requirements. So when we talk about the non-real requirement, they do not becomes very stringent in design, and even there is a deviation from the timing constraints satisfiability. We can survive, but for hard real-time system, we cannot survive when we miss the any timing constraints, and therefore we need to have a better techniques to predict about the behavior of any system at design time. It's not the runtime; it's a design time, and therefore the formal verification is something which is very important for such design of such kind of systems. Now we have various techniques for the verification, right? And sometimes we call the validation also. There is always a discussion about the difference between the verification and validation, and it's very difficult to really define a because the crisp boundary between the two. So we have deductive verification, model checking, equivalence checking as a formal verification because they are based more on mathematical foundations. The simulation is of course is being used very extensively in the industry, right? And because it is little simpler than the formal verification and can be applied easily to any environment. Okay. Simulation, prototype design, right? This is also testing is also. Right? So we'll discuss a little more about these things. So as I said, deductive reasoning, theorem proving talks about mathematical concepts. Model checking also talks about the mathematical concepts. Same is the equivalence checking. Now, why do you need a verification? So system complexity, difficult to manage, more time, effort devoted to verification than to actual design, need automated verification methods and integration. These are some sort of issues, right? We are struggling to design a better techniques for the formal verification or validation. Why we need the verification as we are discussing, because many systems are time critical systems, and when we talk about the time critical systems, right, there is always a danger for loss in terms of life, in terms of money, and so many things. We'll have some examples, right, which can really tell us, right, what and why we need a verification techniques. So we need reliable hardware because it's not the formal verification is not for only for the software, but for hardware design is extensively used. It's much better used than the software. So your formal verification techniques are heavily applied in a hardware design. Maybe processor, may it be a memory, may it be any component of a computer system. Simulation, as I said, is a very commonly used and easy method, but as we say, test cannot handle all possible cases, or right. So, simulation at times is being not trusted also, right? In the literature, when you submit your result based on the simulation, there are always questions whether your simulation environment which you have constructed is correct or not, right? Or you have designed your model, the simulation and modeling is being done something in a bad manner to simply generate the results. So formal verification conducts exhaustive exploration of all possible behavior. This is theoretically correct, but practically this is a very difficult target to achieve. Right? So we say explore some possible behavior. If correct, all behavior are verified. If incorrect, counterexample, right, presented. And there are some examples which are available maybe for theoretical, but may not be used in the industry. Okay, the reason is being because they are not fully matured or limited to some certain verification aspects. So we have a model checking tools just like SBM, Upal, Corona, Mocha, Spin, and there are some more. One is I think Prism, and there are more. So many model checking tools have been designed by the researchers, and some of them are being partially used in the industry also. Similarly, we have a tool checker or the theorem prover. These are the automated tools. Now we say we have a large number of applications, right? So the application encompasses many domains. Some are given here: transportation, commerce, industry, right? So many things. So here what we say, in contrast to your PC, faulty behavior in such system can be very costly, right? So we'll discuss why the faulty behavior, and from where this faulty behavior will come. This will come from your bad techniques of modeling and bad techniques of your you can say the verification, right? So we have some examples here because designing systems error made corrected and they are detected. We like them. Generally, later error is detected, more costly it will be solved. Okay, so we are talking about the handling of the errors in the system and what can be the consequences of those errors if you deal them at a different later phase of the development. So this is some sort of a diagram which says, right, whether you are dealing with the your errors are being identified at the time of the requirement gathering or the analysis, whether they are being identified at design time or coding time or testing time, right, when the system is placed in the field. So you can see the cost of mitigating the faults or the errors if you happen to identify those errors at a later stage. So later the stage, more is the money involved in handling those errors. And there are some examples, right? I think everybody remember floating point division unit of the Intel Pentium chip was faulty. And then the company has to take all such your computers back from the people. And it has costed the Intel nearly $500 million. Now we can think of a small error which has gone undetected due to the wrong verification techniques has resulted a loss of $500 million. So we can understand the requirement of the formal verification techniques, right? And then apart from the economical necessity to find errors or faults, there are systems that are mission critical or safety critical. I think by now we have understood what mission critical and the safety critical systems are, right? These are the systems where time becomes a very important consideration, right? So if you are not going to take a timely decision to control your system, the consequences are disastrous. And therefore, right, the verification and the validation tools becomes very, very important for all these systems. Another instance is there is a loss of nearly $5 to $7 billion where when you have this flight control system named Avian, right, high rocket being destroyed after 40 seconds of its launch, right? So just you can understand how much efforts and money has gone to that project, and it just has been wasted within 40 seconds. So, right, we can understand the need of the verification techniques, and that too very robust formal verification techniques, or maybe the robust simulation techniques that is we need. Now, design problems and the issues. Now, when you design any system, right, there are many questions in your mind, right? So there are many kind of the requirements which we have studied in our software engineering. So some of them are written here: functional correctness, performance, testability, maintainability, domain analysis, requirement capturing, design space exploration, design for test and debug, project management, and so many things, right? I think the people know about the life cycle development of software, any software, right? So more or less same case goes in the system development also. So the question comes here: how would you ensure the correctness of the different phases of product development? Now we'll discuss a little more on validation and the verification. So let us try to understand what is the difference between the verification and the validation. The people or in the literature, these two terms are sometimes being used interchangeably, but there is a difference, little difference in these two. So verification frequently defined as the activity to answer the question: are we making the system right? Okay. If you change the order of system and right, the verification becomes validation and validation becomes verification. So at times it is very difficult to digest, right? What is the difference between the verification and the validation? So are we making the right system, right? So which one comes first, right? So verification is the primary step at the time of the design, to verify different aspects of a design. The validation can be performed after the product has been designed. So verification is a formal analysis, and we say validation is an informal analysis, because the verification is based on the mathematical foundations, right? While validation is not. By verification, we mean the investigation of the truth of the statement about the model or the system. Because generally we do prepare a model for the system, we do all kinds of the right? You can say the reliability checking and other aspects of the model, and then we really develop a product based on if the model is correct, we convert the model into the product. Furthermore, we call a method formal if it is based on the rigorous, well-defined mathematical. Right? It is used to do the more general investigation of the suitability of the conceptual solution for its purpose and goal. This is some sort of a diagram which it talks about the validation and verification, right? So informal requirements and conceptual solution, right? Executable models and formal requirements. And so somewhere we need the validation techniques, somewhere we can resort to simulation and the validation technique. And it depends. Right? The system design and availability of the resources with the system, or availability approach for the validation as well as the verification, right? The formal verification is the investigation of the defined relationship between the formal representational system and its requirement. But more important is, right, formal verification does not directly apply to the system that is being designed, but only applies if the requirements have been captured correctly and the formalized model is an accurate representation of the actual system. So the last sentence is very, very important. If your model is not correct, right, your analysis will not be correct. Now, when you prepare the model, right, it can be very abstract or it can be very detailed. Depends upon the kind of the application we have in hand or kind of the approaches we have in hand. Sometimes if a system is very, very small, the abstract nature of the model suffices the other requirement. But if the system is large and it is time critical, then I think the detailed model becomes very important. The next is to automatically verify certain aspects of the design. So do we have a tool to do the automatic verification? That is again a question mark. If you have, you can do some aspects manually or physically, and rest of the can be done right automatically using the tools available. Some requirements, for example, right, deadlock. Okay, the absence of deadlock is because deadlock is the most common discussion, and the system should not enter into the deadlock. So we always design a system, right, which should not go into the deadlock. Now, once it has been analyzed whether the formal model satisfies the formalized requirement or not, the result can be interpreted for the actual design. Okay? So first you have to formally verify the design which you have prepared. Okay, or the requirement and requirements you have to verify whether whatever the requirement you have gathered are correctly put into the order, and then you prepare the design. So I think we are well familiar with the software engineering. So these are the formal steps. Okay. And as I said, the verification can be partially automated also. So now we have some techniques where we can do the partial automated verification, and rest of the thing can be done through simulation or through manual. So we can combine both the technique simulation as well as the partial, as well as the formal verification. So now the people are advocating also the simulation where the system parts which are not very critical or time critical, you can go and test through simulation or verify through simulation or validate through simulation. And the part of the system which are really critical ones, I have to go for the formal verification also. Okay. This is simple end. Now we'll talk about modeling behavior of the real-time systems. So many techniques exist for verification of distributed real-time system, ranging from manual inspection of a design to formal verification method. So there are some form we have written, textual or graphical description. We are very used to this kind of representation of the model. So we prepare the textual or graphical description of the system, right, or the model, right? We sometimes resort to the pseudocode. We write the pseudocode for the different functionalities, right, and then we do some sort of a after modeling do the simulation, and then finally you can have the formal specification. So we want the formal methods, right, but because of the limitations, right, of the you can say the converting your model into the mathematical form, right? This formal specification, formal verification of each and every task is not possible, and therefore we can use the combination of the different techniques to ascertain the reliability as well as the correctness of the system, right? Some of the concepts or the techniques used for the formal verification or formal specification are given here. So formalism may capture structure and architecture aspects of the design or focus strictly on the behavior aspects, right? So formalism can be used for these two things, right? But we are more interested in the behavioral aspect of the system when we go for the formalization or the formal verification. The biggest problem in designing the formal verification technique is the state space exploration problem. Let's understand what is state space exploration problem is. The major problem in verification of distributed system is the enormous number of their potential behavior or states. So we say we have an n component and every component has a n internal states. So the total number of states available with the system is the n to the power n. And therefore, this n and n can be very large. So this exponential, right, state space is a problem when you go for formal verification application, right? So it's not only time consuming, but the techniques to deal with this kind of the problems are not still existing. So how to minimize the state space without compromising the reliability and the correctness of the application design, and then applying the formal techniques to this state space, right, is really in need of the hour. And the researchers are extensively working on the automated tool design for doing so. Since verification entails checking and certain requirements pulled under all possible circumstances, all behavior should be explored. Right? Because we can't say that, okay, now I'll test only 20% or 30%, right? Uh, so we say since verification until although this in specific cases number of states to be explored can be reduced significantly or certain classes of variables can be examined, right? All at once, the global trend is unavoidable. All right. So you can't say that I'll test only half of the states or the one particular application states and I leave the another one. You do not know which right behavior or which set of states can lead to a faulty design, and error can right encompasses to your system design and will create a problem in the future. So states are providing central problem to the verification of distributed system. Designer is unable to foresee all potential interactions. Then simulation do not cover the entire state space, and the forward method that to cover the entire space better with resource constraints such as computer memory and time requirement for verification. Because another important aspect is simulation, you are not going to remember the states. But when we are doing formal specification, all these states or the history of the system has to be stored in the computer memory. And therefore, if your state space is large, your memory requirement and computational demand is more. Okay, so therefore they are also a problem. And the time is also a problem. Okay, so we say model and the temporal logic. So we can use the temporal logic for the verification of these models which we prepare. In order to verify these systems for properties they possess, we need a way to effectively capture the desired and undesired behavior. A formulas to express properties of a system behavior should not only be able to express statement about such observable feature, but should also be able to relate them over time. Temporal logic is a popular framework to express such aspects of the system behavior, right? And several variant of the temporal logic are there to deal with the different kind of the applications, as I said. They are the non-real-time systems as well as the real-time systems are there. So the temporal logic which we are using for the non-real-time system is not suitable for the real-time system design. Okay, so therefore different kind of the temporal logic has to be designed for the different type of the systems, right? So I think do we have a 5 minutes break?
Yes, sir.
या कंटिन्यू रखना है
सर नहीं ले लेते हैं सर.
चलिए ओके तो 5 minutes
Yes, sir. 5 minutes.
ठीक है
Okay. Thank you, sir. Okay, dear participant, if you have any questions, you can ask in the chat box, and at the end of the session, we will ask with the Professor Mahesh and Govind sir.
Hello.
सर ऑडिबल सर वेलकम बैक सर
हाँ शुरू करें
यस सर
ओके Okay, fine. So, right, we were discussing regarding formal verification, need of the formal verification. So, there are a number of analysis techniques for the systems which we design or the models which we design, right, for any system. So, some of them are written here: peer review, right, simulation, testing of realizations of prototypes, and formal verification techniques. So as we know, in peer reviewing, an colleague who is not involved in the same design inspects the design code and check it manually for mistakes, right? Although this is an effective method to remove number of mistakes, but need the automatic techniques, right, to examine the design, because manual inspection for a small system is fine. But if the system is of moderate size or is very large, then of course this technique is not suitable. Okay, so we cannot rely on the peer reviewing techniques of the analysis, right, or correctness of the system. Now, simulation is something which is used very extensively, not by the researchers but by the industry. Okay, because this does not require the mathematical formulation of your various requirements or system specifications, right? And therefore, at times become easier, because if you are comfortable enough with your the programming languages or the system requirements, then you can construct a model, and then through simulation, if you can test. But of course, the demand is if you go for more formal method, it is always better. So as we said, the simulation are easy to use and can be largely automated. I think everybody knows about the simulation systems, just like CloudSim or Aneka, and there are many more for different systems. There is a different simulation. Online simulation systems are also available. Validation of the simulation result, however, is often ad hoc and manual. As I said, if you have a formal method, if you have proven the model and the system requirement or system specification using formal methods, then there is no question mark as far as the correctness of the system is concerned. But if I am using the simulation, right, there is always a question mark whether the modeling and simulation technique which I have used are really correct, or it really addresses all the requirements of the system, right? May it be non-timing or maybe timing requirements. So sometimes we say the simulation is ad hoc and manual. It generally does not provide answer to the post verification questions. It can expose erroneous behavior, but the absence of bad behavior cannot be guaranteed, right? So if your simulation techniques are very, very good and exhaustive in nature, then they can really identify the error in the system and you can remove them. But at times they might go undetected, even the best effort of the designer or the team. Another problem with the simulation method is that in practice it is often not based on the well-defined semantics. So semantics sometimes not even be defined for the simulation environment. Okay, so or if they are defined in ad hoc manner. Interpretation of concurrency, communication primitive, and the real time are often not made explicit, but are affected by the simulation model or construction of the simulator. It does suffer in terms of coverage and error detection capabilities, right? the complete state space may not be covered by the simulation model which we have prepared. And as I said, the error can go undetected. However, the advantage of simulation method, they are scalable. Okay, so does not suffer from the state space explosion problem in the sense that large models can still be simulated. This makes it possible to use a single model for all simulation type analysis. As the design or requirement changes, it is easy to re-evaluate the new model with respect to new requirements. Okay, so as far as the use of the simulation method is concerned, is easier as compared to the formal methods, and therefore, right, it's more common in the industry. So we say analysis technique that is being used extensively and effectively in the industry is the simulation. Okay, so testing and prototype. Prototype are often used for verification, right? So, but at times the prepare the prototype is costly and therefore it's a seldom used technique. The prototype is close to actual realization and thus highly adequate model. A prototype can be executed in real-time speed, which is often impossible for simulation model. However, the design must be almost ready before a prototype can be built, and the process is time-consuming and expensive, right? And therefore, right. So at times the system is very, very large. Preparing the prototype is very difficult. So this prototype design and the testing can be applied for a smaller project, but for large projects becomes very difficult. Model can be built and analyzed quickly. Both simulation and testing are usually non-existing in the sense that not all possible behavior are exercised and checked for conformance with the requirements, right? So both simulation and this prototype testing techniques are called non-exhaustive. While on the other end, the formal verifications are called the exhaustive techniques, right? So non-exhaustive methods are cheap, easy to use, and flexible. This makes them very suitable in the initial stage of the design. To quickly evaluate design alternatives and obtain a quick impression about the correct behavior of the system. So the simulation is therefore extensively used by the industry because of some inherent advantage. But nowadays we are talking about to form the amalgamation of the simulation and the formal verification. So it is possible to have the techniques which combines both and use the characteristics which are good in both the techniques, and an exhaustive technique can be prepared for the system which can guarantee a correct design of the system. On the other hand, formal methods are a mathematically based technique and tools for specification, design, and verification of the systems. Formal methods originate from a more ambitious and more fundamental than practical approach to the system specific design. It provides the vehicle to reason mathematically about the correctness of our design, and therefore they are more reliable. This allows a mathematical proof of its correctness, right? The use of a formal method forces designers to make their ideas about a design or its requirement very precise, and this uncovers many errors, right, already. So at the time of the design, if you are very serious about your thought process, then right, the designing the formal methods also becomes easier because many errors can be identified and the formal methods can be designed to more you can say the serious errors in the system. Integration of the formal methods into industrial practice remains limited. Right? This is caused by a number of issues that hinders their practical application. As I said, right, because these are based on the mathematical foundations. So design is of the formal method is really very, very difficult. So the issues which are have major concern is one is the state space explosion. The intrinsic hardness of the verification problem and the desire of most verification method is to produce a definite answer, make it a big effort to keep the state space within the reasonable size. Right? So for dealing with all the states available in the state space, as we have said, it's not only time consuming, but designing the techniques or the mathematical tools is very, very difficult. Maybe because of the resources, maybe because of the limitation of the mathematical foundations of the designer, right, or the team which is responsible for the verification of the specifications, right, as well as the design, right, the final product. Automata have a reputation to be hard to use and to require the user to be knowledgeable both in advanced mathematics and also in the internal operation of particular tools. There is a lack of industry strength tools. In particular, there is a lack of tools that integrate in the entire design flow and tools that are used. Right? So these are the major reasons why the formal methods are not adequately available in the industry to various aspects of the design. Now, properties of the formal method, it should be unambiguous, should preserve the consistency or satisfy the consistency requirement of the system, must satisfy the completeness, right, and the soundness of the system, right. So soundness, generally we say whatever the automata you have designed, right, it should satisfy the formula, or all the states of your system should satisfy the formula, right, of the automation. And correctness is the formula accept precisely all the state sequences that satisfy. So formula must satisfy all of your states. So these are the major requirements of your formal methods, and we have to prove mathematically all these properties of the formal methods. Now, for the verification technique based on the formal method are model checking, and these are the two major, you can say, the verification techniques. So model checking is a procedure to check the correctness of the system by traversing the entire state space whilst looking for erroneous behavior, right, expressed as the reachability of a particular state or by formula in temporal logic. Okay, so erroneous behavior, right, expressed as a reachability of the particular state or by formula in the temporal logic. A big advantage for model checking is that it is completely automatic. So once the mathematical modeling is done, you can make an automatic tool to do the model checking. Model checking has been applied successfully in the field of communication protocol and hardware verification. So we are well familiar. Especially hardware verification, this model checking is very prominent and being used extensively. It is particularly suited for control intensive and less for data intensive systems. If the check of the particular requirement fails, the model checker tool provides a counter example with which demonstrates this. The state space exploration and struggle against it often require that a new model of the system is made targeted towards the requirement that is being checked. Such models are thus not optimized for readability but only to reduce state space. As we have said, state space is a problem for this formal verification. Therefore, the efforts are to be made to reduce the state space so the analysis can be performed. It's not for the readability of the solution. When the design changes, the abstract model has to adapt accordingly and the verification has to be repeated. So it's not as simple as the simulation. We have said if there is any change in the design, the adoption is very simple as far as the simulation technique is concerned. But when it comes to the formula, the formal verification, right? So the things becomes a little more complex. Now we can see that there are some commercial tools, right, which can do the partial model checking, and they are available. I think we have an example of these kind of tools from the system, maybe used. So Spin is one, and then we have SBM, Mocha, Upal, like Kronos, and Prism is something which right is being reported in the literature very extensively. So these are there. This is some sort of state transition diagram. We are well familiar in computational theory or automata theory, and then this can be converted into the this your computation tree. So right, there is the execution in the any system goes infinitely. So this you have a task. We can say the system should have a capability to do the task continuously, right? Unless until the task finishes. So our this automata must present the infinite presence of the activities or the scenarios. This is one example which has been taken right from some paper. This traffic light controller. So if you design some traffic light model for the traffic light controller, then you have to analyze and do the analysis for various aspects of the controller's correctness. So right. So model checking, safety conditions, and the fairness condition. These are the two things, right? So safety condition means no green lights on both roads at the same time. So we have to build a logic for this condition, right? So you have to build first logic and then you can prepare the transition diagram, and then you prepare the computational tree, and then try to analyze whether this safety condition is being satisfied or not. So there are some, you can say the Boolean relations or maybe some other mathematical concepts can be used to represent the safety condition as well as the fairness condition. And these two conditions has to be proved also. The writing the relation or the theorem is not enough. You have to provide the proof of the correctness. So whether the safety condition which we have specified here is really being satisfied in all kinds of the scenarios by the system. Similarly, the fairness condition is being satisfied by the system design or not. These has to be checked. So some sort of analysis is being given here, right? So going in detail. Okay. So the second approach, as I said, is the deductive methods, right? So deductive method such as theorem proving, correct requirements are formalized as theorems in a mathematical theory which describes the system's behavior. I think we are well familiar with the many aspects of the system design where we put the things or the requirements of a system in terms of the theorem, and then we prove that if this theorem is correct, and if that theorem is satisfied by the system, we can say as far as this property of the system is concerned, right? The design is correct. Okay, so in real-time systems, when we do the suitability analysis, we generally go for the mathematical relationship for the suitability test. Okay, and then we can say, okay, now this mathematical condition is being satisfied, then I can guarantee the task is not going to miss their deadline, right? So writing the hypothesis or writing a theorem is fine, but the proof of the theorem is equally important. So when I put my requirements in terms of the theorem, in terms of lemmas, or in terms of some mathematical relations, I have to prove that those mathematical relations are being held under all kinds of the circumstances. So I have to explore the entire state space of the system, and then I have to show that my theorem is going to be correct under all circumstances, or be true under the entire state space. So we say a requirement can be shown to hold by proving it correct term, right? Deductive methods are able to deal with finite states and parameterized system using inductive proofs. So induction principles can be used to prove the theorems also. This makes them better suited for the data intensive systems. Theorem proving tool assist in construction of such proofs and try to construct the proof autonomously. Generally, such tools are not powerful enough to produce large part of it, such proofs entirely, right, autonomously. Usually the crucial steps of the proof have to be invented by the user, and the theorem prover might be able to fill in the smaller steps. Right? So the biggest, you can see the bottleneck is right. It requires the trained people and a lot of manual efforts to construct the proof in minuscule steps and can be checked by the tool. So you need a expertise to design the formal verification methods in this category. Of course, we can have some automated proof checkers. So some names are, I think, are there. So we have HOL, we have NGTHM, and then PVS, and then Isabel, and these are the some automated tools which are being designed by the research community, but they are not, you can say, these generalized ones or can satisfy the requirement of the system. Therefore, these methods are not, you can say, very common or not very, you can say, popular to be used. And therefore, it says designing the deductive method which are automatic is very, very difficult because it needs a manual intervention and the manual expertise, and depending upon the application design. So the use of the deductive method is really very, very difficult for the formal verification of any system. Another problem is the theorem provers are less suitable for debugging as debugging tools than model checkers. They do not provide much insight if a particular theorem cannot be proved. The fight against the state, space, explosion, and preciseness required for formal method make their application typically relatively time consuming. Okay, so the time is another factor, right? So they are not very common. This makes it hard to deal with the aspects of real world design process where specification changes and requirements are trade-off. Okay, so if any change made in the requirements, I think your theorem or the lemma which you have designed may not be suitable for the new requirements. You have to design the new theorem, new lemmas, and then have to provide the proof of the correctness, right? Again becomes the time consuming, and or you can say the person dependent, right? If you do not have that much of knowledge or the capabilities, right? The producing the method for this category is very difficult. As timing or the probability issue come into the play, formal technique become harder to use. As I said, designing real-time systems, especially the hard real-time system, or generalized technique is not still there. Right? The research community is really striving very, very hard.
ஆமா ஆமா அதெல்லாம் ஒரு பண்ணு சரி பண்ணோம்.
So we'll discuss
நல்லா இருக்கும் இல்லையா
the comparative analysis of FM, the formal methods and the simulation. Right. So we have already said simulation practice are flexible, use capable of dealing with large systems at a small level of details. So we have said we are too ad hoc and at times need a manual intervention. Formal methods are precise, give definite answer to the verification questions. Formal methods are good at exploring subtle errors that tends to escape verification by means of simulation and testing. FM are limited by the state, space, explosion problem and expensive to use in particular when design and requirement change frequently. and re-evaluation of all the requirements is required after such change. Right? So this exhaustive formal methods to detect more subtle error that is not exposed by very particular interaction and are likely to go undetected by simulation. So that's why I said we can use both together, simulation techniques as well as the exhaustive formal methods to design the system, right? And that might create a much better system or the correct system. Now, how these real-time system verification becomes difficult, we have already discussed. So we have said now there are large number of embedded systems ranging from small to large size, right? Which have a real-time system requirements. If they have a real-time system requirements, the techniques to verify those techniques is really very, very important, right? And therefore, we are looking for the formal methods for verification of the real-time system requirements. Now, real-time system model checking is computationally more expensive and therefore suffer even from more state space expression problem. Although the gap between the untimed and timed verification algorithm is getting smaller with the advent of more clever techniques and improved data structures. Theorem prover can also be used, but theories and proofs becomes more complicated. So I might give some little example from this category tomorrow discussion for real-time system design, where we'll discuss the problem came into the one of the spacecraft and being later solved, and the correctness of that protocol is being provided by the deductive method. Now, this is an example which tells about the need for the real-time system verification. So, the kind of error that may occur are illustrated by the event which occurred during the NASA Jet Propulsion Laboratory Mars Pathfinder mission in July 1997. Although the mission was successful, right, and was able to provide the data to the ground station, but there was some problem with this. So all these things are there. We say activity of the rover were controlled by the number of software tasks running on a real-time operating system. And this was a priority-based system, of course. So we have a time-critical system to schedule, right? And then we have a watchdog for monitoring the various system activities and reporting to the ground station or to the controlling station, and to take the necessary, you can say the steps whenever there is problem in the system. The software task share the certain resources, mutual action mechanism to control of the resource was implemented. Scenario which occurred was actually well-known problem in the sort of system, right, called the priority inversion. So what the priority inversion is, everybody knows, right? If a low priority task stops the execution of the high priority task, then we say there is a priority inversion, right? So this Pathfinder, at instance, the lower priority task was in possession of the shared resources, which are being required for by the high priority task. So while occupying the shared resources, the task is interrupted by a medium priority task used for the processing of the data that is being collected, right? So high priority task time critical task is started and requires the use of the shared resources. It can not access the resource, right, since the lower priority task was in critical section and right, having the resources which are being required by the high priority task. The lower priority task in turn cannot be activated to complete its business with the shared resources because it is suspended by the medium priority task. Now the problem here is because you have a three tasks in the system. One is a low priority task which is in critical section, right, and have a synchronization requirement with the high priority task, and therefore the high priority task was blocked due to the shared resources in the exclusive mode. But medium priority tasks have no conflict with the lower priority task as well as the high priority task. And when the lower priority task is in execution, the medium priority task comes and no resource conflict is there. Therefore, it preempts the lower priority task, start execution, and lower priority task is in a waiting mode. Now, in between, the critical high priority task comes and then it wants to execute. But because the lower priority task was also suspended and holding the resources, the high priority task cannot be started. Now, what happened? We have said lower priority task as well as high priority task, both are critical tasks having some specified deadlines. And medium priority tasks may not be a critical task or hard deadline task, and the execution time may be large. So what will happen? The high priority task is being indirectly stopped by the medium priority task. Okay, and the duration of the medium priority task might be very, very large, resulting in the loss of deadline of the high priority task. Okay, and the system might be in problem. So this priority inversion may result in a problem of the system, because we have not taken the due care at the time of the analysis, right, to bound the waiting time of the high priority task due to this resource synchronization problems. And that was the problem which is caused in this Pathfinder, and the Pathfinder has to reset whole system and then it has been restarted. Right, and there might be some loss. So later they say they have redesigned the task, uploaded to the system, and then the Pathfinder has done its work, because it's nothing like that. The Pathfinder has been restored for this small bug. So that was the, of course, is the we can say it's not too dangerous task, right? Otherwise, if something is wrong, the Pathfinder might have been damaged. So what was the conclusion of the team there is, Glenn Reeves, one of the designer of commenting on the problem. Our before launch testing was limited to the best case. I think if you remember in the beginning, I said whenever you are going to design the real-time system, it has to be a worst case scenario. You cannot go even for the average case scenario to design a system. It has to be worst case scenario design or worst case design. So high data rate and science activities. The fact that the data rate are from the surface were higher than anticipated, right, serves to aggravate the problem. The time taken was much more than anticipated at the time of designing the tasks. So deadline which you might have enforced on the task was not correctly done. We did not expect nor test the better than we could have ever imagined the case. So they were also a little bit of in a easy mode, and then they said, okay, now everything's fine, and let us launch this vehicle to the space. What is the problem? It shows one of the difficulty of verification and lack of the practical formal methods for the temporal logic approach for model checking of real-time systems, because they might have resorted to simulation where this problem has gone undetected, right? Okay. If we could have the more automated formal methods for real-time systems, the each and every aspects of the software or the algorithm or the protocol which has been designed for this application could have been checked, and there may not be the problem which has occurred on the Pathfinder. Okay, so the model of the environment during testing contains some implicit assumptions that turns out to be incorrect. Okay, so if you made some assumptions and if you have not tested them well or not really confirmed, right, with the conformity of the actual environment, the system is bound to be failed. So the formal methods are very, very important for both system specification and the verification of the requirements of the system. Now,
we have various branch of the formal this methods, right? So we'll discuss a little more and then okay, we'll break after some time. So automata theoretical verification, a powerful approach towards the automatic verification of linear temporal logic is called automatic theoretical approach, right? And then we define another thing which is called the tabular method for linear logic table, right? So we convert this linear temporal logic into the finite state automata, and this conversion is called the tabular method. So we'll discuss tomorrow a little bit more on the tabular method. The tabular method for real-time temporal logic, traditionally linear temporal logic, describe quantitative temporal properties of the system behavior. It relates only the order of events. Extension of the logic exists that can also refer to the quantitative temporal behavior, allowing the distance in time between events to be measured. The practical tabular method are exhausted the class of real-time temporal logic formulas, right, allowing the verification real-time temporal logic properties using timed automata. So we have untimed automata as well as the timed automata. So some of the terminology which will be used tomorrow in the discussion when we'll discuss this timed automata. So one is your label transition systems. We are well familiar with the this automata theory, transition assigned or state assigned kind of diagrams. Okay. So here we say we have a LTS, labeled transition system, right? So we have a nodes as states, and then ages are transitions. We call them the labels generally. So a little bit of new terminology is being used in the formal verification. And then we have some requirement which has to be specified. So you might need to represent the deadlock into the system, and therefore deadlock is something where there is no age from one node to the, or there is no progress in the system, right? So when there is no progress in the system, there is if a state in a deadlock, then there is no labeled age to the next state. Okay, so the edge is missing if there is a deadlock in the system. Divergence means your system can execute or can go from one state to another state, and therefore we define, right? So as is, small as is difference the state, and then capital as the set of states. Okay, and then we say we can go from the one state to the another state depending upon the behavior of the system or the levels. Then we'll have some sort of the set of propositions where we have different requirements being put into in the form of the propositions, and finally they are being converted into some formulas. Okay, and then these formula has to be satisfied maybe by your this linear temporal logic, or maybe by your automation. So we'll see. We also define a new automata called the omega automata. So we have a finite automata which have a finite states. So if you have a infinite words, then we say the same automata can be termed as the omega automata. Right. So the states in this automata is termed as the locations, and we label the locations rather than the transitions, and we label them with a set of symbols instead of a single symbols. So they are the two kind of the logic which is being talked about. One is a linear temporal logic. It can be timed, it can be untimed. And second one is the metric interval temporal logic, which is being used for the real-time specification as well as the proof. There is some example which gives a little the state sequence of the propositions, right? So whether the formula is satisfied or not, and then some insightness of the state sequence. What we mean by this state sequence is given here. And I think we can break here, and from tomorrow a little bit we'll discuss about this real-time temporal logic and how it is different from your linear temporal logic, which is being used for the untimed activities or untimed LTL. Okay.
Sure,
So,
sir.
questions here?
So, participant, do you have any questions? So, if you have any question, you can ask now.
Because see, it's a long time which I have not gone through, but I'm thankful to Kumar and the team that they have given me an opportunity to really learn a little bit more about this, because I have read this automata theory and the computational logic long back, nearly 20 years back. And revising the concepts is really, but what I have realized is at times we feel why we are teaching this automata theory or computational theory to the students, but while preparing for this lecture, I realized this computational theory is really very, very important in the modern system, especially for computer science. No?
Yes, sir.
So I think everybody has to really look into, especially the research scholars can find the new applications in especially IoT or what we all call the cyber physical systems, where the providing the correctness proof is very, very important.
So, good afternoon, sir.
Good afternoon.
Actually, sir, I have a question. Mars Pathfinder. Actually, you talked about a priority inversion
Yes.
problem. So, sir, how did they solve that problem?
No, I'll discuss tomorrow. Earlier, I thought I'd discuss in detail today, because they designed the two protocols. One is called the priority inheritance protocol, another is called priority ceiling protocol.
Yes.
And probably earlier they used the priority inheritance protocol where they have not tested that carefully. So there was a two problem. Your PIP has this priority inheritance protocol run into the deadlock, as well as the time delay, or the, you can say, the there is no bounded delay between the two activities. Any task which might be critical can be blocked by the lower priority task for a longer time, undetermined time. So non-deterministic nature of the PIP was also noted. And then finally, after realizing these two problems, they developed the PCP, priority ceiling protocol. So tomorrow, if I get time, I'll discuss a little bit, because it's a very beautiful protocol. They have proved that protocol's property also by using of formal methods only. Okay, they have not used the simulation method. They have used the deductive methods for proving that it will not have the deadlock problem, as well as the delay whenever the PCP is being executed is bounded. So they have given a proof of both bounded delay as well as the free from the deadlock.
Okay. Thank you, sir. Thank you. Thank you very much.
Therefore, I say I also believe this your formal methods are better than your simulation.
Yes, sir. Yes. Thank you, sir.
Any question? Because at times I'm finding our research community is very much afraid of this real-time systems also. Okay, because at times you need to have more mathematical foundation for designing the solutions and then proving, and So I think now, because of your cyber physical systems, you have to anyhow ascertain the real-time requirements, because each and every small application of your cyber physical system is having a critical activities, time critical activities. So that is also important, and I think I should congratulate both of you for having very apt topic and the timely topic, so that other can be inspired to do some research work in this area.
Thank you, sir. Thank you very much, sir.
So I think there is no more question is there. So
Okay.
I just want to say thank you to you for such a valuable and informative talk related to real-time system, as well as some deep knowledge about the formal verification from the starting scratching. Okay, and I hope it will help all the research scholars which is available in this particular audience, and they will find it interesting, and this will help them to go further. And hope we will be in touch with you, sir, for for our guidance. And I think tomorrow will be there again one more session at 2 p.m. So we will taking it positively. So we will meet tomorrow, sir. And I wanted to say thanks on the behalf of all
Okay,
the
thank you.
Department of Computer Science. Thank you, sir.
Thank you.
Have a good day, sir.
Thank you, sir.
Okay, dear participants, the feedback link will be available on your chat on Google Chat Meet. Okay, so kindly fill that one. And next session will be at 4:30 p.m. and Professor S. Ramesh will be available for their valuable talk. So be on time. So thank you for such a lovely audience. Thank you. Okay, so there will be a feedback. Okay, and wait for just 2 or 3 minutes. It will be available on your chat. Okay, and there is no need to go for the attendance because this is Google Meet. It will take automatically. Okay, thank you. Just wait for 5 minutes for the feedback link. Thank you.
Good morning, sir.
Good morning.
Good morning, sir.
How are you?
Fine, sir. How are you, sir?
Good, doing good. This is one more day is there or this is the last day?
Sir, one more day is there.
So how many days totally?
So 5 days.
5 days. Okay.
Yes, sir.
It was supposed to have been in the campus. Now it's online. Fine.
Sir?
It has become an online event or always it was planned as an online event?
No, sir. It was planned as an online event.
Oh, okay. So every day, how many hours of?
Sir, 2 sessions are there
Hmm.
and 2 hours each.
I see. 2 sessions, 2 hours each. So 4 hours per day.
Yes, sir.
Hmm.
So,
And participants are mostly students or also from only from your college or how is that?
no, sir. It is from all over India.
I
So,
see. Okay.
most of them are students,
Hmm.
and very few of them are from different universities. Means assistant professor and lecturers.
I see. Okay. Okay.
Okay. So, good afternoon to all, and good morning to Professor S. Ramesh sir. So, sir will continue his lecture from the last session where he finished. So, it's over to you, sir. Thank you, sir.
Thank you very much. And it's a pleasure to be back. And are there any kind of quick questions or anything that
So, participants, if you have any question, you may ask, sir.
or you can just post it so that you can
Yes, if you have any question, you can put it on the chat box, or you may directly ask, sir. sir, I think there is no question. You may continue. Thank you.
Right, that's right. I'm just. Okay, so let me continue some parts of that. I think yesterday I went up to finite state machines. Right. So I think I had talked extensively about the role of finite state machines and then how it can be extended to include some structure, and there are a lot of extensions to state charts. State charts had been successfully used in the industry, especially in aerospace, and to some extent, some of the ideas of state charts have been taken over by other model-based designers, and then they have been incorporated in other languages like STRL and Simulink state flow. Right, that the term state flow comes from MathWorks. There is actually a state chart version of you can think of as MathWorks. Right, so there are various possibilities explored in extending state charts, adding code to transitions, adding code to states. Code means that you could use programming language code like C code, C++ code, and so on. You can enhance with complex data types and function calls, and there are also efforts in combining textual programs with state charts. Various commercial tools exist, as I said, StateMate and Rhapsody, Stateflow from MathWorks, and various UML tools and STRL technologies. This is in the aerospace industry. This language was very useful. People have used sync charts, a version of state charts called sync charts. Right, so here is, for example, just to give you a flavor, one could have this kind of descriptions in state charts. Just have this, this is a state, an AND state. Again, this elevator controller AND state, having two concurrent states separated by this dotted line, dotted vertical line. And you have the mixture of states, transitions, and also some kind of sequential code, right? So within each state, there are instances of code segments or code fragments that are inserted here. Right, I think in some sense, state machines are good in describing compactly the notion of state and transitions between those states. Whereas now when you have expressions, mathematical expressions for capturing transformations, state transformations, and then programming languages are useful. Right, so I think this combination of the relative expressive powers, you can combine them together to your advantage. Right, I think here is a brief segment of how a version of state charts called state flow, right, in Simulink appears. So you have, again, you see that 4 concurrent states, and there are each state is actually another state machine involving its own state, default states, state names, and transitions. And then transitions are labeled with, you can see, for example, one of the transitions if we take, right, so this talks about O2 fail and O2 normal, for example, on the left-hand side, left topmost. There's a transition from the state named O2 fail to the state named O2 normal. And this transition is labeled with some conditions called ego greater than max ego. Right, that's a condition. under which certain actions might be sensor failure counter is incremented. That is the action being done, right? So in general, the form of the labels are you have some events, external events that are triggering, and there could be a condition and the state of the system, and as a result of which you can do some actions. And you can also see that in each state there could be some kind of entry actions and exit actions. For example, when you're entering O2 normal, you are making an assignment statement there, right? O2 state equal to 0, right? Like that, you can enrich the state machine concept with all this, programming language, traditional programming language statements. Right, I think besides the notations, all these have precise semantics. You have using the precise semantics, you can actually do an execution of the state machine, for example, right? So there are simulation engines. So MathWorks provides simulation capabilities of state flow, using which you can actually give sequence of inputs to the system that is described using Simulink and state flow, and you can see progression of states and so on during simulations. Right, so you can take traditional standard concurrency problems that you might have studied in the context of operating systems or networking. You can try to create state machine models of that, right? And the most important thing about state machines is that they are formal objects, so they can be subjected to formal analysis and verification. Right, there are other models like synchronous reactive models, useful for expressing control-dominated applications, and rich primitives for expressing complex controls. Again, SREL from SREL technologies. Right, these were useful for describing hardware circuits, for example, and also for small embedded control applications. So you should think of model-based approach. Modeling languages are not, in some sense, universal, unlike programming languages, right? So depending upon the application, I think I was talking about in response to some questions yesterday, depending upon your specific application needs, people go and develop small modeling languages that provides abstraction necessary for the application. So that's why modeling language, those who are involved in developing and then using modeling languages, they use the term meta modeling, which means that you define your meta models are essentially definitions of modeling languages, right? Even if you take UML, UML is considered a meta modeling language. You always define profiles in UML, right? UML is a kind of universal. I think originally when it was proposed as a kind of universal meta modeling language. What does that mean is that you can define small profiles within UML using UML constructs. UML provides constructs for defining meta models, and each meta model corresponds to a particular modeling language that is unique to or that provides necessary abstraction for a given application. Right. I think another thing is that why different modeling languages are there is because the kind of application might also drive the type of modeling language that you'll use. There are, if you look at designs of systems, there are control-dominated designs, like hardware controllers, embedded controllers. These are control-dominated. So then the notion of state transitions, they become important. And there are also data-dominated designs, right? Like data flow languages, like your DSP applications and so on. Right? In the case of control-dominated designs, input events arrive at regular and unpredictable times, and time of arrival and response more crucial than actual values, right? You are not doing a lot of transformations on the values, but more of, if I receive this input, right, I'm supposed to respond with this output and so on. In contrast, data-dominated designs, the inputs are streams of data coming at regular intervals. sample data. Now, this is in the context of data of embedded systems. Values are more crucial, and outputs are complex mathematical functions of inputs. Right, so this typically appears in numerical computations and digital signal processing computations. So that's why there is a modeling language based on data flow models. Right, state machines, state charts, STRL are good for more control dominated designs, whereas data flow models are useful for data dominated systems. They're essentially a special case of concurrent process models. Right, you have processes and then concurrently compose them to create system behavior. Right, so system behavior described as an interconnection of nodes, and each node describes transformation of data. Connection between a pair of nodes describes the flow of data from one node to another. Right, data flow models, these are often graphical languages. I think one of the motivation for defining specialized modeling languages is that it should be intuitive to the particular engineering people who are not designing these systems. It should be intuitive to them, and it should provide support for simulation, debugging, and analysis, and also code generation. Right, these are some of the aspects that I emphasized. We want to provide the necessary abstraction. We want to provide an early means of easily developing, analyzing, and then revising, and so on. And also, finally, once you are through with your analysis, exploration, and so on, you should be able to easily generate code into the specific target platforms. And in the case of systems involving both hardware and software, you would like to have this hardware-software partitioning. So there are many commercial tools available using data flow models. Loose signal are some of the examples. Simulink, if we take, which is being used in automotive embedded systems and many embedded domains, is actually a data flow language. Right, data flow models are a different way of looking at computations. Computations triggered by availability of data. Right, this is in contrast to sequential control model, where the system stays in a particular state and waits for some inputs. And data flow models are essentially inherently parallel, suited for parallel executions, natural for signal processing and continuous control applications. There is a fundamental mathematical model underlying data flow models. They're called as Kahn networks. This is a very well-known modeling framework. So here is a very simple abstract example of a Kahn network. This network consists of 3 nodes. Right, these are not to be confused with state machines. These are not states of a system, and the system stays in one of the states. These are actually processes which you can think of them as concurrently running. And these processes are connected by what they call first in, first out, or queue channels. Process 1 is connected to process 2 and process 3, and the process 2 is connected to process 3. So which means that in general there might be some input processing, or there could be some generators. Process 1 could be generating some data. Right, so imagine that now we are in the embedded domain. So none of the processes are terminating process. They will be keep generating something, keep executing. Right, the result of executions are typically triggered by either internally by generation of new data, or it could be externally through the channel. For example, process 2 keeps waiting for some inputs coming from the channel connecting process 1 and process 2. Once it receives something, it will do some transformation on the data and then send some values through the channel between process 2 and process 3. The same way that process 1 can generate some data and then push these data through these 2 channels, and so on. Process 3 might be a consumer. Now it might be consuming and then doing some external actions, which is not described here. Right, this is also one of the very well-known models, typically used in the kind of DSP kind of application, digital signal processing applications, where you get a kind of stream of data, processing of those data, and so on. So you can think of this, each process is to be doing distinct functionality, right? I think one of the reasons for not using sequential code and using this kind of traditional programming language construct, and resort to these kinds of higher level abstractions is that they provide a natural means of giving some abstract primitives, which would be useful for application engineers. Right, and I think as somebody asked yesterday, so in principle you can do everything in a traditional programming language, but in a traditional programming language does not provide necessary abstractions for your applications. The programmer or the engineers will have to create their own abstractions and then follow the discipline. Whereas these meta modeling languages provide these abstractions naturally, so the engineers can directly use them. Right, I think so here is just to give an example of DSP-like applications. Here is a kind of data flow networks in a kind of different, slightly modified syntax. Now you can think of them as on the left-hand side, ABCD as data streams that are sending some numerical data. They are sending some data, and then you have operators like plus, minus, and star. So the node plus actually receives two inputs from A and B and then adds them and then pushes that added value to channel T1, right? These edges are called channels, and nodes are essentially computational nodes. They might be doing some simple functions like plus, minus, or star. These kind of data flow networks are useful in one context. In fact, if you look at hardware design, from design to implementation into hardware circuits, these are very useful abstractions. So you convert higher level VHDL or Verilog model into this data flow networks, where each of these nodes are performing very simple functions. Right now, this kind of description is very useful for doing what is known as implementing on as AND gates and OR gates and so on. Right, so this kind of, you can think of this as modeling abstractions that is easy, that is useful for not for the end system developer, but for intermediate design of converting design into efficient implementation. On the right hand side, slightly more higher level abstraction is there. Right, these nodes need not do some simple primitive functions like plus and minus. They could do, for example, complex operations. Data here there are indications of DSP operations like modulation, convolution, transformations, and so on. Right, so there is a very precise description of these data flow networks. Like each process executes independently. Execution involves read, compute, write cycle. Reading consumes the data from the inputs, 5.4. Writing adds data to the output, 5.4. And unbounded 5.4, right? Unbounded queues are assumed. But in practice, you might put some assumptions on the length of the queue and so on. But the process code is sequential. You could use any imperative language like C++ for describing your process execution. Right, so then how do you implement this data flow network, right? So when you talk about the reason why I'm talking about this implementation is that one is that it should provide the abstraction, it should provide a mechanism for precisely describing your computations, so that it is better than writing it in natural. It's much better than there should not be any ambiguity. There should be clarity on that. I think that is one of the fundamental properties of modeling languages. And it should be executable also, so that whatever computation that you are describing, you should be able to simulate them and then ensure whether what you have described performs the intended functions, right? So you should be able to, it should have a precise semantics. So that is why, for example, that's a precise semantics for data flow networks. which describes that when different processes are executed, what happens to a read instruction inside a node when there is no data? What happens when there is no space in the output for FIFO? Supposing you have a bounded FIFO, then what happens? Does the process wait or not? The modeling language will have to precisely specify those details. And if you have multiple inputs coming into a node, there has to be a precise description of which channel to read first, right? So, and there are different execution models. You have to talk about execution models or semantics. Data-driven models and demand-driven execution models are there. You could also bring in non-determinism, right? So I was talking about in the context of finite state machines. Now there are good reasons that why non-determinism is allowed, right? Ultimately, at the level of implementations, non-determinism may be undesirable. But at the level of describing computations, right? That is the level of abstraction that one has to keep in mind when you are designing modeling languages, right? So even non-deterministic results could also occur. So if you take Conn networks, they have been defined to be deterministic processes. Reading an empty channel blocks the process in the sense that the process waits. So the read operation is also called wait. Simultaneous waits on multiple channels not possible. So these are some details, technical details I will not go into. Emptiness check on FIFO not allowed, right? So whether a channel is empty or not, that's not being allowed in the Conn network. Each process is a C-like function augmented with wait and write operations. Right, so here is an example from a very classical, I think this Conn's network is a very well-known theoretical model. So in the 70s and so on, when people are defining computational models, Conn network was very fundamental there. And so even though it is as old as programming languages themselves are, it has been used in the DSP context as a modeling language. Right, so here is a node, right, from a Conn's network, very interesting one. So you can see that the process, the function f that is being computed by this node is described in a C-like notations, right? So it can refer to, for example, so there is an integer declarations like internal variables like I and boolean b, and so you can have you check for some condition like b, and then wait on u, else wait on v, right? You can conditionally wait on one of those channels, and whenever you get some value, then you go and print, and then now maybe take the value of input, and then maybe change your state, right? So you alternatively wait on the two channels and then send it. Now this is what is called as merge. Now if you see that this function is doing what is known as alternative fair merge, not even fair merge, it's in fact round robin merge, right? Initially it waits on u, and whenever it receives a value from u, it goes and pushes that value to w, right? And then it waits on v. In the next cycle it waits on v, gets a value from v and then sends it. So it's a kind of alternate merging of, you can think of function f to be merging these two channel values u and v, streams of data that is coming from u and v, and then sending it out via w. So what is this function doing, right? So you can here there is an input. Now G is essentially taking input from the channel u and then sending via v and w. So this is in some sense complement of the previous one, right? So essentially it is taking a stream of value from the channel u and then channeling it through one of those output channels v and w, again alternatively, right? So this is one simple nice way of describing this. This is if the previous one is called merging, right? So this is essentially it's a kind of forking kind of thing, right? right? So you can you can construct complex networks using this, right? So another thing that I wanted to say is that, see, these are now you can see that I would like you to see that abstraction that is provided by these kinds of nodes. Now, if you have to write these computations, in principle, you can write them in C-like language, but you will have to go and write lot more piece of code than what you are writing here, right? Here, all you need to do is that draw these networks of nodes and then write some piece of code for individual nodes, right? And then when you put them together, really complex functions can come in, right? So here is a process network consisting of nodes like the same nodes G and F, and then H1 and H2, right? So you can think of this H1 as might be generating. For example, it emits in a value 1, in the sense that H1 puts in the initial state, when it starts, puts a value 1, whereas H2 puts a value 0, okay, on their output channels, on their respective output channels. Then F and G are the previous functions. You can try to imagine that what is happening here, right? So what will happen? One and 0 is being produced, and that is being F is essentially sending it via their common output channel, and then G is again diverging them, and then there's a whole lot of computation that keeps happening, right? Once you send one value, generate one value in the beginning, then a whole lot of values are being generated through this network, and then the network never terminates. Right? Now, scheduling is very important aspect. Now, one has to do careful scheduling. Scheduling means that these concurrent processes, how to schedule them. You can convert them into a sequential piece of code. Schedule different nodes so that no unbounded accumulation. Now, it might happen that if you wrongly schedule only certain node, now if a node is generating a lot of data and then you keep scheduling that particular node, that channel might get unbounded, right? So you need to schedule them so that both consumers and producers are scheduled uniformly, right? Different schedulings are possible. So you can think of all schedules being equivalent or not. And now you can ask the question that given an arbitrary network, now interesting computational problems also arise. Given a conv network, can one execute in bounded memory, right? So one of the issues that might happen in a network like this is that now if you don't schedule them properly, right? Because these are concurrent processes they're executing. Now scheduling corresponds to which process runs faster. Now, so to say, right? If one particular process is going to run fast, it might go and flood the network and so on, right? Flood a channel. So these are some interesting theoretical problems one can think about. But as far as implementation is concerned, you have to ensure that the modeling language has to define these semantics precisely, define these scheduling mechanisms carefully, so that when the user describes some computation, right, he means it has to have a precise semantics. So there is a interesting language called synchronous data flow models. So it's called SDF. This was conceived in the labs of University of California, Berkeley. And now this is essentially restriction of conv process network to compile time scheduling. Rather than scheduling it dynamically at runtime, this allows you to schedule them in compile time, which means that you can translate them into sequential programs. So each time in this network, for example, each time a process fires, it reads a fixed number of reads and writes from and to its input-output channels. It's very natural. It has been proved very natural for multi-rate signal processing, right? So you can convert them. The underlying semantics is a kind of a data flow equations. So again, there are some interesting problems that comes in, right? So if you have two nodes A and B that are connected, A reads P tokens and then produces M tokens, right? So it's not only reading one input. You could also even specify that whenever A does some computation, right? A reads P tokens and produces M tokens. B reads N tokens and produces Q tokens. If N1 and N2 are the number of firings of A and B, after which no tokens in the FIFO, right? You want to make sure that FIFO is empty and so on. So then you can form such equations. So essentially every data flow program, right? You can think of this as a data flow model, and every model corresponds to a set of equations, right? So in general, each edge in the network will define an equation. No hanging of input-output channels, which means the source and destinations are modeled as nodes, and an SDF underlying model, right? So I think so there has to be an underlying execution model, and that is what the compiler is going to do, right? Essentially, compiler takes this abstract high-level descriptions and then converts them into a set of equations, and that equation gets solved, right? So you can think of this model as a declarative specification of your intended functionality, right? So you have to make sure that a network of the data flow nodes corresponds to a unique solution, right? If you have multiple solutions, then that corresponds to non-determinism. If there is no solution, that corresponds to a bad, it's like a kind of wrong program or a wrong model. Right, I think there are some theoretical aspects or compiler-related things one can do with synchronous data flow models. So I will not go into the details. All I would like you to get is that these modeling languages provide, like finite state machines, this data flow network, synchronous data flow networks also provides a level of abstraction in which people can describe their computations as a set of sequential processes, and these processes interconnect through channels, and there is an underlying semantics or execution model. And in fact, there is a framework. There is a simulation framework that is provided. It's called Ptolemy, right, which allows you to execute this, generate these systems of equations, and then these equations can be solved. And when the solution exists, you have a kind of simulation. You can simulate these data flow descriptions, and then you can you use that simulation to debug your data flow programs or data flow models. Right? There are certain interesting examples. Now I have just given. Right, for each model, there is a set of solutions, and depending upon the label. So, for example, if you take on the right-hand side, model 1, A, B, C are 3 nodes which are connected, and A, when it is running, essentially can produce 1 token via one of the channels and 2 tokens via the other channel. And B, where receives 1 token from the channel connecting A and then produces 2 tokens. And similarly, C receives 1 token from the upper channel, 2 tokens from the 2 channels, and then does some internal computation. Right, then you can actually form nice equations like A is equal to B, 2A equal to C, because 2A's, so essentially, looking at how many tokens are needed for firing, you can form equations. Every edge corresponds to an equation. Then you can solve, is there a solution exists? Now, what is the least positive solution that exists? Right, that defines a schedule. Now, for example, in model 1, so you form this equation A equal to B, 2A equal to C, and 2B equal to C, and then try to solve, right? What A and B values, and what is the least positive value, right? For example, A equal to B equal to 1 and C equal to 2 solves this problem, which means it corresponds to a particular sequential execution of these nodes. Like first fire A, then fire B, then fire C, then again fire C one more time, then again repeat this. Right, so ultimately you can convert this data flow node descriptions into sequential programs. So you can think of this ABC, once you have computations inside ABC described using, say, C functions. This is nothing but the schedule or the execution of this model corresponds to a C code, right, which is repeated. Right, and there are certain data flow models like the one probably, is there a schedule? You need to ask the compiler. There is a target code generator. Code generator, it's not called compiler in the context of modeling languages. You call them code generator. Code generator does this analysis, creates these equations, generates these equations, tries to answer the question that is there a solution that is possible. If the solution is not possible, the code generator is going to come back, or the simulation engine is going to come back and then tell that this model is wrong. So you have to go and revise it. Right? So that way it gives you some kind of compile time feedback. Right? You can think of them as syntax errors in your program or semantics errors in your programs. Right? If there are no errors in the program, then this program is compiled into a low-level sequential code that can be executed on any machine. And I think this is what is described in this slide. So SDF scheduling involves forming the equations, obtaining the least positive integer solution, which gives the schedule. Right? The equation may be inconsistent, in which case the program or the model is wrong. Right? Now, there could be deadlocking, right? Because whenever you have concurrency system and then you have now processes waiting, there could be deadlocking. Deadlocking is a kind of, you can think of them as some kind of an error. Right. So I think this is another kind of, I just want to give you a kind of flavor. It's not that only finite state, you should not take the view that modeling language means that they are only finite state models. So finite state systems, finite state machines are one kind of modeling language for control dominated designs. For data dominated, you have this data flow equations or CON network kind of models, SDF, synchronous data flow networks. You could have discrete event models. Now, for example, VHDL and Verilog uses what is known as a discrete event model. Again, here the models are interconnections of nodes, but each node reacts to events at their inputs. The values are not very important, but events are very important. Right? External events initiates a reaction. Delays in nodes modeled as delays. Right? Delays in event generations. You can do simulations, and there could be problems with cycles also. So, right, these are some technical problems. Once you get into the modeling language design, there are some issues like schedulability, deadlocking, cyclic executions, and so on. I think these are some details which are not necessary for the moment in this class. Right, discrete event models again have a kind of pictorial descriptions like A, B, C, D. So these are essentially processing nodes. These are looking for some events on their inputs, and then they can trigger new events, and the whole thing can be cyclic. Right? Again, cyclic execution is fundamental because these are reactive systems. Right? Here is an example, just to give a kind of concrete example. These are not theoretical notions. If we take Simulink, Simulink has a kind of combination of discrete event and data flow. So here is an example of a Simulink control descriptions. You can think of these rectangular boxes as nodes, and there are inputs to these nodes. There are edges or channels or where events or tokens can pass through. And essentially, this is a fuel control system described using Simulink-like language. So in fact, if you look at typical automotive engine control designers or many other control systems domain, people write their programs in this high-level language. Right. So inside, for example, this essentially gives. So you see that here is another description of one of this description, high-level description, fuel rate controller. It's described using Simulink. There are blocks like control logic, which is a data flow data flow node. You have a fuel calculation, another data flow node. They are all interconnected through channels. If you look at control logic, there is a state machine-like construct is there. In fact, that is actually a state flow node, right? That inside there is a state machine. In fact, the state machine that is there in this control logic is the one that I talked about some time ago, right? So you can go and not this complex state machine. This complex state machine is actually inside this control logic, right? So this control logic, the state machine inside is essentially that state machine. These inputs, if you see that there is an oxygen, there is a speed input, there are various outputs. These arrows indicate inputs and outputs, and some of the outputs could be to the terminal themselves. So people write these kinds of complex combination of these nodes, interconnection of these nodes. Nodes can be hierarchical, so nodes can contain further subnodes, and then so on. At any level you can go, and some of the nodes could be state machine models, right? So even though I described state machines and data flow equations as separately, but in real descriptions you will get hundreds and hundreds of such nodes for describing a control logic involving multiple modeling formalisms. So if we take MathWorks Simulink State Flow, which is a very well-known modeling language used in the industry. So it uses Simulink, which is a data flow model, and it also uses state flow, which is a finite state machine-based model. Right. So just to summarize, so various models we reviewed, sequential programming models, hierarchical and concurrent state machines, data flow models, and discrete event models. And each model is suitable for particular applications. State machines for event-oriented control systems, sequential program model, data flow model for function computations. And real systems often require a mixture of models, as I said. Now, modeling tools and languages should have a combination of all these features. And I think this is something I was talking about. Berkeley has a tool called Ptolemy, which allows you to combine different modeling languages. You can take their execution models, combine those execution models. You can define new combinations of new models for your embedded applications, right? These are some of the references from which I have drawn this material. So if you go to MathWorks website, you can get more details about Simulink State Flow. Right? These are some of the classical papers on more theoretical treatments on what you need to have. Now, what are the right kind of modeling primitives that are required for embedded applications. Okay, so this completes my one important part of my lecture on model-based development. Right, what I gave is a very high level view of what you need to look for in a modeling language. What are all the important things, and gave some flavor of 2 or 3 types of modeling abstractions provided by some of the well-known formalisms or platforms that exist. Okay, so this completes my one section. So we can probably pause here and then ask, provide some opportunity for participants to ask some questions. Are there any questions?
So participants, if you have any question, you may ask. So, sir, I have a question.
Mm-hmm.
So, sir, can we say that all these systems means a time-triggered system?
Okay, so I think you are touching upon an important aspect of event-triggered versus time-triggered, right?
Yes.
So, I think again it depends upon the nature of the applications. So if you take state machines, data flow equations, you can, there can be two modes of defining them. You can make them time triggered also. You can also make them event triggered also, right? So the difference is, how you are going to do, the execution model decides that. You could associate a clock tick, right? Clock to either a subsystem or for the entire system. And then when you are going to read an input, right? In the case of state machines, you go from one state to another. So you might do that in a kind of event triggered fashion whenever an event appears in the system, now by abstracting out time, or you could also do it in a kind of time triggered one. So it's the difference between these two are very, very fine. So you can think of a time triggered system to be an event triggered system with a kind of special kind of clock tick as the event, right? So if you are going to associate a clock tick to every transition or every computational execution, then it can be time triggered, right?
Okay.
So I think both modes of executions are possible.
So another question is, what is the research aspect of scheduling in concurrent computation model?
Okay. Right. These are some of the classical ones. Many of the research in data flow computations and so on, they have been done, already done. Now it's a kind of, somewhat in the 80s and 90s, a lot of development in these areas. Of course, one of the challenges is verification, right? People here spend time on providing modeling languages, execution mechanisms, and so on. There are some interesting problems like large networks, people can write. For example, if you take Simulink state flow, people design systems involving hundreds of blocks, and each block may have 3 to 4 levels of hierarchy. And some of these blocks are state machine blocks involving tens of concurrent state machines, and each of them might have 5 to 8 states, right? And these are for real applications. They might be embedded with a sequential piece of code and so on. Right. Now, how do you take this large state machines, large data flow equations, and then prove them, right? They satisfy the given specification, right? So this, if you want to do rigorously verify and validate, there are some challenges, right? So that is one kind of, now if you're talking about formal methods, which is the kind of focus of this workshop.
Yes.
You could also think about testing, right? Supposing that you are testing a large Simulink state flow diagrams. How do you go and measure coverage? Or how are you going to execute, how are you going to generate test cases that have sufficient coverage, right? How do you find bugs in a given system? These are some of the challenges. We do not have foolproof tools that exist today that would take any arbitrary Simulink state flow diagrams and then property and then check them correct all the time, right?
Okay. Yes, sir.
So these are some of the verification and validation problems always remain because of the size and complexity of the system that we are talking about for realistic systems, right?
So, is it a solvable problem? Means, can we solve it? Like if you are taking a Simulink model and verifying it, means any arbitrary Simulink model and you want to verify it, is it a solvable problem?
Right. I think, see, if you look at now all these programming, all these modeling languages, however nicely they started with, in order to cater to the needs, right? So one of the aspects of the modeling language, one of the constraints for the modeling language is that you should be able to go and generate final code, right, which can run your embedded control system. Right. As a result, these modeling languages have been made more and more complex by including variables, right, assignments, and then you have cyclic computations already exists, and these variables could be as complex as you could even include the entire C language variables and C language constructs and so on in the edges and transitions. As a result, many of these modeling languages have become not Turing complete, right? So once the moment you have that, any arbitrary piece of computation can be described. You have the traditional issue of undesirability, right? That is one issue,
Yes, sir.
right? Even if you restrict it to kind of finite state part, then there is an issue of size, right? So if you take hierarchical concurrent state machines, right, concurrency is easy to compact, it is compact, but the computation wise, it is going to explode, right? So the same state explosion problem that you know, that you might have heard of in the model checking and that kind of techniques, those things will happen even here for realistic large systems.
Okay. Okay. Thank you, sir.
Okay.
So, is there any question, participants? I think no, sir.
Okay, so now I will switch gear. So long I gave something more foundational or fundamental for cyber physical systems. More on why do we need modeling, what modeling achieves, and some flavor of existing modeling languages, and some of which are also practical, right? So now I'm going to give to some extent answer some of your one of your questions. Now, how it is being used, what are the challenges of using this in an automotive context,
Yes, sir.
right? I thought that since you invited me, there has to be a flavor of my application domain coming and playing some role, so that the students and others are excited about what is the value of all these things, where it could be used or applied. Okay, so my next talk is going to be talk on that. So can you see my slide?
Yes, sir. Yes, sir. Yes, sir. It is.
Okay. Okay, so I'm going to focus here in the next maybe 40 to 50 minutes on automotive software testing and validation, right? So the focus of this workshop is testing and validation, and what with my expertise in formal methods, verification and software engineering and so on, what I have been doing, and what are the challenges in automotive software, right? To some extent, it relates to the question that you asked.
Yes, sir.
Right. So these are just to give you an example that some nice pictures on. If you see, you might have heard of in the automotive context, driverless vehicles, right? Autonomous vehicle and so on. If you look at on the left-hand side, you see a kind of model of a fancy vehicle, and this was a concept vehicle, right? I think it was conceived maybe in the 1950s or something, right? I think that the person who is standing next to that vehicle is actually, I think, it's a kind of chief technical officer at that point of time in GM, right? It's actually at the backdrop of a GM campus. And people were in General Motors, people were talking about or thinking about driverless, self-driving vehicles even as early as 1950s or 60s, right? Now, even though now people talk about it, in the recent times is appearing to be becoming a reality and so on. But it's a kind of age-old concept, right? Now, leaving everything to machines and then the human being wants to relax and so on. So even in those early days, in the early days of not even computing had not developed into subject, people are talking about driverless cars, right? So that's what on the left bottom you see. Whereas on the right top corner you see a lot of concept, a lot of the new generation right? Many of these are prototype vehicles that were used for, again, it may be 10 years or 15 years old. Some of those are concepts. Again, those vehicles, if you see that, you see standard cars, but fitted with a lot of equipments, some of which are very, very complex, some kind of radars and lidars and multiple cameras and so on. They're all fitted with that. And if you see that, some interesting vehicle on the rightmost corner, that's a prototype vehicle conceived in GM. It is something like just only two passengers can sit there, and there are no, it will drive automatically. It can go from any place to any other place, and these vehicles can communicate with each other, right? So that you can now avoid congestion, you can avoid collision and so on. This is just to give you a flavor that this is what the evolution has been from fully mechanical system to a kind of it's transformed into electromechanical, and it's becoming more and more electronic and software vehicle, right? So what I'm going to talk about here is whatever my observation in this company for the last more than 10 years, being part of the R&D. Right. So I would like to tell you that today's vehicle is actually a kind of software driven. Right. So automotive systems. Now, when we talk about automotive systems, even though traditional view of automotive systems is it's a kind of mechanical engineering object, but it is becoming more and more electronic and software. Right. I think engineers like many of you are going to play an important role in building these systems. Right. Some of the elements that you learn out of this CPS will be fundamental to them. They may not directly help you, but fundamental to you for a kind of better understanding of these systems. So here, coming from the automotive area, so I emphasize on automotive, but similar things can be talked about in the context of aerospace, aircraft industries, and so on. Right. So automotive systems are exploding in complexity, size, and criticality. Connectivity, right? Just like vehicle to vehicle, vehicle to infrastructure connectivity. AI machine learning components are also becoming important components. And verification and validation does occupy a major part of this development effort. Testing continues to be the primary means of validation, right? We are trying to enhance whether we can improve on testing with more rigorous verification and validation practice. Right? Software testing has many limitations, focused on bug finding, costly, slow, inefficient, elaborate infrastructure, typically done at the late in the design stage. Right? 262, there are a lot of standards that are coming in order to develop, right? In order to develop vehicle and then put them on the road, you need to conform to certain regulatory standards. In the context of automotive, it's a kind of self-regulatory. And there are some bodies like ISO bodies who go and who are the members of whose are essentially automotive company experts. Right, so I participate in some standards committee. Now many of my colleagues also participate. 26262 is one such standard. It recommends so very rigorous methods for validation. So complementary approaches to validations are needed. Some of which you might have learned in this course, like static analysis, symbolic testing, formal verification, correct by construction, runtime monitoring, and so on. So many of these approaches are emerging, and there are a lot of adoption challenges, which is what I would like to highlight in this talk. So just to give you some idea, right? This is again, I prepared these slides, so maybe 2 or 3 years old, slightly dated. Right? So total number of vehicles produced crossed 1 billion in 2010. They say that we'll cross 2 billion by 2035. Every year, more than 50 million vehicles have been added. 84 million in this was 2 or 3 years old. in 2015, 500 millionth GM vehicle was produced. And now if you see, more than 50 million vehicles recalled in 2014 and 15. Right? Vehicle recall means that they get some bugs. After they were released to the market, people started using it. Right? These vehicles were recalled, some of which were due to software bugs. Right? There are cases where exploding airbags. Right? Airbags are one of the important safety components in vehicles. Whenever it is involved in a crash, right, for the driver or the passenger's protection system, you have airbags which will explode and then save lives. People have seen that with airbags, people's lives could be saved. Now sometimes, but if the airbags explode at the wrong time, that may cause injuries and sometimes death also. Right? There are cases where the airbags explode at the wrong time, or they don't explode at the right time, right? Or emission issues, right? Pollution is also very, environmental and pollution issues are also becoming very, very important now. And there are strict quality measures that are being imposed by various, regulatory bodies, in India and in other countries also. In Europe, it's even more very restricted. In America, I think it's even restricted and so on. So these are some of the issues for which controllers are being used, right? In order to control, in order to excite, or in order to explode an airbag, you need control systems. In order not to explode, you have to be looking for some events to happen, whether a crash event happened or not, right? And when you are driving, certain measurements are taken on the exhaust gases. Based upon that, certain cleaning functions might be excited, might be initiated and so on. Right? I think if you look at control systems, were introduced in automotive systems from in the 70s. Right? Automated control of IC engines. Right? Now, if you see on the right hand side, there is a small control system that was introduced by Volvo for the first time in automotive in the 70s. And I think this diagram is from I think Wikipedia. So just to control internal combustion engine, right? Controlling an combustion control engine is a very complex task. It started with when to initiate, when to start the spark in a spark plug, right? The fuel has to be injected into the chamber, and when the fuel and the air gets mixed at the right level, then at that point of time, the spark has to be created. Right? I think that is how, in order to create, that was a very time-critical operations. I think people started using control systems in that context. Then it slowly expanded. And today's engine control system, so you can imagine that today's engine control system consists of thousands of software components involving more than 20,000 to 40,000 variables, program variables in that software, right? Thousands of functions are there. All of them constitute the entire software, right? So from single microcontroller-based development, hundreds of lines of assembly code, that was the beginning. But today, exploding feature content. Now, if you look at down in the right-hand side, so many features have been added into this, many of which are now clubbed under what they call as advanced driver assist systems. Now, and also called active safety systems to today's autonomous driving, right? So essentially people have come to the stage of driving the vehicle without a driver, right? So if you look at this, carefully look at this diagram on the down, the amount of complexity is measured by the number of features that you have, right? So you have this engine control system, you have electric power steering, right? So today's steering, right, it's no longer manual, right? The driver intends to steer then that intention is captured. There is a sensor that is capturing that, whether this driver is intending to steer left or right, and then there is an electric power system that comes into comes handy, so that you can very easily turn the wheels, and so on, right? Adaptive lighting, adaptive cruise control, right? So you have heard of cruise control, CC, which essentially you set a speed and that the vehicle is always running at that speed. You have adaptive cruise control, where you not only control the speed, but also you control the spacing between your vehicle and the vehicle ahead of you, right? If you come too close to your vehicle, then actually you slow down, and so on, right? These come under advanced driver assist systems, right? Automatic braking. And there's a kind of variety of features that have been added into today's vehicle, most of which are happening thanks to the development in electronics and software, right? So every automotive company has their own roadmap from ADAS to autonomous systems, right? I think initially it had a kind of modest thing of engine control system. Now we are talking about, at some point, a lot of driver information and alerts, right, have come into, and from no control to limited control, like emergency intervention. Now there's a whole package of driver assist package that are available. So limited on-demand automation, right? So in a kind of limited context, right? So if you take highway driving in the Western countries, they are highly regulated. So you can actually let the machine control your vehicle. Now there is a concept called super cruise. I will talk about it in the next slide. So from monitored control to transferred control, right? So essentially, you can think of, you can leave the control to the vehicle, not just like in the aircraft. People do that, pilots do that. Now pilots are only monitoring the system. Most of the time, it's being controlled by the machine. Similar things have come into automotive. And people are talking about autonomous driving. So every company has its own roadmap, right? So if you take active safety, these are some of the packages like driver awareness package or driver assist package that are available in today's vehicle, like lane departure warning. If the vehicle goes away from a lane, there is a warning. Forward collision alert, side blind zone alert, rear cross traffic alert. There are advertisements you might have seen that when you are reversing the vehicle, if there is another vehicle or another pedestrian, it can actually go and do a. One is alert. You can also do a braking, right? Similarly, driver assist package, another full speed range ACC, right? Adaptive cruise control, collision imminent braking, or emergency braking to avoid contact, and so on. And here is a new feature that was introduced a couple of years before by GM, for example, Super Cruise. Some of you might be aware. So it's doing not only adaptive cruise control, but it also tries to keep the vehicle within the lane, right? So you can see on the right-hand side, an engineer, in fact, this is a colleague of ours in R&D, now who was involved in the early development, prototyping of this feature. So if you look at him, he's actually driving the vehicle with his hands folded, right? His hands are not on the steering wheel. So the idea is that this vehicle can do limited steering, right? It can do lane following, and also it can avoid collision, and it is going to keep the vehicle within a lane. Of course, it's in a kind of limited setting. In addition to doing that, it will also be monitoring the driver, whether the driver is awake or not, because this feature, under certain conditions, it might hand over the vehicle to the driver. So in order to be safe, the driver has to be all the time alert. So it will be monitoring the driver, whether the driver is watching the road or not. And whenever the driver is distracted, right, it looks for certain signs. And when the driver is distracted, it's actually going to beep and then quickly ask the driver to take over the control, right? all these things are possible only because of the electronics and software. Right? So this is another V2X. Technology allows cars to communicate with each other. V2V, V to infrastructure, and V2P. Even people are talking about communicating with pedestrians and so on. So many of these are used for safety applications. Right? So V2V, for example, hazardous vehicle warning, emergency electronic brake lamps, curve speed warning, work zone warning, pedestrian awareness, cyclist awareness. So starting from 2017, these kinds of V2X applications, safety applications have come, and people are talking about using it even for actual control of the vehicle. Right? There's a whole lot of what they call as 360-degree sensing. Now you have long range, right? Now today's vehicles have, some of these vehicles have long range radars, short range radars, LiDARs, and multiple cameras. To have a kind of 360-degree sensing, they have an awareness of where exactly they are in. You have maps inside the vehicle. Today's vehicles have, some of these vehicles have maps so that they know the location where they are in. They can do what is known as localization, right? Up to the lane at which they are in, right? Even people are talking about very high density localizations and so on, right? High density GPS and so on. Sensor fusion, V2V and V2I integration. Right? All these things are possible, right? From active safety to autonomy, as because of the software. And look at this complexity of this software. So nicely described by the synopsis slide on the right hand side. Right now, look at this picture. Now, so you can see that some rectangular blocks, and then crisscrossed with some lines. So this is essentially picturizing the complexity. Each of these blocks, you can think of them as complex software functions, which themselves might have tens of other functions. These crisscrossing lines are essentially interactions between these software functions. Now there is an enormous complexity increased scope for faults, and failures are noticed, right? They are not only safety critical, but sometimes even business critical, right? Business critical and turning into safety critical leads to loss of image, confidence, and sales. So if you look at the automotive system, they are deeply embedded systems, right? They are actually called as systems of systems. They are real-time, possibly safety critical. Now examples, some of these are electronic power steering, brake controls, powertrain, active safety. They have complex software architecture, and right, they are deeply embedded systems. And they can be moderately, there are systems, multiple systems are there within an automotive systems. There is a deeply embedded subsystem. There's a moderately embedded subsystem, and systems like closely real-time. Example, body control, instrument panel, and heating, cooling. They are all moderately embedded. Some amount of real-time controls are required. Some development tools, for example, Rhapsody is being used. Right? In the case of deeply embedded systems, Simulink State Flow is being used. So this is just to relate to that model-based development that's being used. The software architecture is AutoSAR. Lightly embedded systems is non-real-time systems, which has it may have DSP-like applications. Security is very important. Infotainment systems, right? Those are lightly embedded systems. Right, and the type of embedded systems also. So you have closed loop control systems, right, based upon control systems theory like PID control and even model prediction control and so on. The tools that are used are Simulink and State Flow, and you have state-based systems also, like body control systems. The control systems that are controlling your lighting and ventilation and windows and so on. These are essentially state-based state transition systems now are being used for describing this. GM uses Rhapsody, for example, for modeling that, and some elements of state flow Simulink also is being used. Again, so when I said the system of systems, different subsystems are subjected to different standards. So you have non-safety critical, which means no potential to cause harm. So they could be safety critical also, no potential to cause harm. So which means that these systems need to be fail safe. They should be able to detect faults, shut down within required fault response times, and so on. So various tools that are being used are, methods and tools that are being used are, as I said at some point of time, DFMEA, right? Now you need to do modeling the fault. You have to make some assumptions about the faults and what is the effect of those faults you need to analyze. And you do complex analysis in order to develop a system and then integrate them into the vehicle and then release the vehicle for public use. A lot of analysis that need to be done. Right. And so another thing is that another feature that I would like to highlight is that these softwares are not being developed in it's a kind of monolithic systems. They are developed as product line. GM, for example, has one of the most complex systems and software product line engineering. So product line means that you don't develop one software per vehicle, right? You develop software for a whole range of vehicles. So you make slight modifications to one product to have a one vehicle to another vehicle, right? So this is the kind of complexity that you have. 3,000 engineers, 300 hierarchical subsystems, thousands of variants are possible, right? So you develop one software, but it has variability, right? Configuration options are there. You set different configurations, you get one set of vehicle, right? And these combinations of configurations make the complexity even more higher, right? And then the size of the code is 100 million lines of code, millions of product instances per year, right? So every vehicle has one software instance, right? Tens of thousands of unique product variants, and a dramatic increase in variation due to new propulsion systems and active safety, right? Different kinds of packages are available. Depending upon the package, you might get, you and me might have the same vehicle, but our packages might be quite different. So the software running in my vehicle might be different from your vehicle, and so on. And these vehicles are being sold all over the world, and different regulatory standards are there in different worlds. So then these softwares are being produced to catering to the different needs of the industry, and so on. And these product lines and the feature sets evolves annually, right? 15 to 20 concurrent development streams are there. So what you see on the diagrams are the different variable vehicles that are being sold by company like GM, right? The software for these vehicles, right, running of 100 million lines of code and so on, these are not being developed for one per vehicle model, or each vehicle model itself might have tens of variations. It might be across different models. You might be using a single software. All you need to do is that vary some configurations and so on. So this is the typical model of development, right? So this is also called as V cycle or V model of development. So you start from concept exploration, and then you have system requirements, high-level design, detailed design, and then software hardware development. Then on the right hand side, you see that the right arm is essentially verification arm, validation arm. So you do the unit testing, subsystem verification, system validation, and so on. And even after the vehicle is on the road, there could be changes and upgrades, like just like your mobile phones getting updated and updated. Even people are talking about updating your software on the field, right? And then they also pose some verification and validation challenges. Right, just give me a couple of minutes.
Yes, sir. Yes.
Okay, I'm back. Right. I think the automotive engineers would like to consider this electronic infrastructure as ECS, electronic. You can think of them as electronics, control, and software. So what do they mean by ECS? Content is essentially the software, the entire software. ECUs, the individual controllers. There are 30 to 40 controllers in a typical vehicle. There could be also vehicles with 70 controllers, right? The controllers are essentially where your control algorithm resides and then taking inputs and then generating outputs. They are also called as electronic control units. Right? I think it started in a kind of modest beginning. There was only one electronic control unit, which not having any software. It was probably a kind of programmable controller, which was used for your engine control system. So today's systems have 40 to 50 ECUs. There are gateway nodes within a vehicle, network buses, sensors and actuators, right? Of course, sensors and actuators are the most important elements. And you have buses like even Ethernet bus. Now people have started introducing Ethernet into vehicles. The earlier one is called controller area network, CAN buses. That's very quite often, quite common in vehicles. Most of the modern vehicles have at least 2 to 3 CAN buses. Now these CAN buses are connected with these ECUs, and signals getting communicated between these ECUs. You have end devices like camera, radar, LiDAR devices, transceivers, right? So if you look inside the vehicle, so you can think of them as any other electronic control system, complex electronic system. So the unique aspect of the process for developing is that ECS assets at every level developed as a product line, right? As I said that you don't go and develop one product, one software. You always develop as a product line. And there's a 3-tier approach to development. You have what they known as electrical electronics architecture, where hardware, sensor, actuator, and networks are being developed. So you design architecture for a whole family of vehicles for the next 5 years, something like that. You do that. Then you have this software architecture. This is middleware-based architecture that's becoming very common now. And then you have feature development. So if you take ACC, supercross, or automatic braking, collision imminent braking, rear cross traffic control. Now each of them are called as features. So the features are developed. So you develop algorithms and codes, and then these individual features are composed together and then run on a software architecture. And the software runs on one or multiple ECUs, and these ECUs are connected to the sensing and actuators. So there is an extensive bench. A lot of time, nearly 60% of the time is spent on validation. Now what they call as bench validation. Earlier they used to be doing the vehicle level validation. So essentially put all the things together and then validate the entire vehicle, whether the vehicle is working as intended, right? So, but this vehicle validation is limited, right? So supposing that there is a bug, how do you trace the bug, right? Where is the bug? How are you going to correct them? You have to redo the entire thing. So more and more upfront verification and validation is happening in the industry. Right? I think this is a kind of typical architecture. So AutoSAR is a very automotive specific architecture that has been developed last 5 or 8 years. This development has taken place. Many of the OEMs, automotive OEMs and suppliers, they are coming together to define this architecture. So this architecture defines interfaces. It even defines some kind of a middleware, right? So there's a runtime environment called RTE, AutoSAR RTE, that defines interfaces. So the AutoSAR software AutoSAR compliant software. So people today, OEMs, try to develop software compliant to this AutoSAR middleware. Application softwares are essentially now your features are being developed with AutoSAR interfaces. So these applications can talk to each other as if there is an abstract communication medium, which is provided by this AutoSAR runtime environment. Below that, you have this real-time operating system which is running on top of your ECU hardware. You have standardized interfaces for communication for various sensors, and also some kind of complex device drivers and so on. So this is typically typical layered architecture that can model the software that runs on a single ECU. Like that, 40 to 50 ECUs might be running. Right, as I said, the software is being developed in a kind of product line fashion. So if you see this V diagram, right, I said that V diagram is the one using which software is being developed. Start from requirements, design architecture, functional architecture, and then individual units composed together, and then unit testing and component testing and subsystem testing, and then entire system testing and vehicle testing. So you can think of them individual features are being developed in a kind of using multiple V diagrams. And electrical architecture, you have V diagrams, and then you compose them together using this composition operator. And then there is a way of configuring them, right? When you configure them, you go and configure them for specific vehicles and so on. So I think that is what is being described by this picture. Right. So coming to testing, which is the kind of focus, right? When we talk about testing, we include model simulation also. Now, I said that model-based development is often used. Model simulation is also considered testing as well as code execution, right? So essentially, testing means concrete inputs used to run the executable system, right? Executable system could be your final C code or models themselves. Right, so you have the standard basic concepts in testing like executable system under test, test data, test oracle, test coverage like functional and structural coverage, black box and white box testing, unit and integration testing, and test bench that supports test execution, test results, and test coverage evaluation and so on. So if we take testing automotive systems, so this is how there are different levels of testing, and you can see that at the x-axis you have this time and cost, resource constraints. On the y-axis you have the accuracy. If you want total accuracy, then you have to have the testing at the vehicle in the loop. All right, that's the rightmost one. So you have the vehicle in the loop testing. You have at the lower bottom you have the model in the loop testing. You develop your model, say Simulink state flow, and take the model and then do the test. Model in the loop means that model is integrated with other models of the physical system, right? Remember the picture that I talked about right in the beginning yesterday. You have the model of the vehicle, model of the plant, you have the model of the controller, you have the model of the network, all connected together, and that's called model in loop. So when you have the model in loop testing at the early stage, then the model is converted into code, into software, and then the software in loop testing. Then you have this plant in loop testing where the real plant, some of the real plant elements, physical elements could be connected to your software and the controller. Then you have hardware in the loop testing, and finally you have the vehicle in the loop testing. So if you look at the new generation where like Super Cruise kind of features, you have even scenario-based simulation, right? So you have extensive simulation scenarios where you can think of a road geometry, you can model the roads, you can model your vehicle control system, you can model other vehicles, you can model pedestrians, and then try to run your system and then see that for different vehicle combinations, road conditions, and weather conditions and so on, how you are going to exercise your control system, how your control system behaves and so on. You can do that. Extensive scenario-based simulation is what people are talking about. Even we have closed course testing. close course testing means that once you have some confidence in the software, you integrate the software into the real vehicles. So there are some vehicles which are at the disposal of the OEM even before it is being released to the public. OEMs, like GMs, they have their own courses, where they can road networks with various combinations of roads, different conditions of roads, and within our campus, where you run the software, you run the vehicle, and then see how the performance of the vehicle is. This is called close course testing, where functionality and performance related bugs are removed. And then finally, even if you take supercruise, for example, it was extensively tested on real roads, right? Because it is supposed to work on real road conditions. So they did a lot of testing with hundreds of vehicles. They hired lots of drivers. The entire supercruise behavior, functionality, and performance of the supercruise feature was tested on miles and miles of testing on real roads before it was released. Right? I think look at the extent of testing. Starting from this, even in the traditional systems, you have been doing extensive testing, and now this testing, the need for testing has never decreased. Right? People are looking for efficient means of testing and verification. I think that's an important need of this industry. Right? So automotive testing, current practice, quite extensive and performed at different levels. You have component level testing, feature level testing, domain testing, vehicle level testing, and so on. Individual features are tested, models are simulated. As I said, the different in-loop testing is being carried out. So model-based testing is something which some of you might have heard of. So essentially, broad definition of model-based testing is use of models in any test step of testing process. Weak MBT, I would like to call it, use of models in measuring coverage of testing over the model elements. Right? You create test cases, and then you exercise those test cases on the models, and then that gives you an idea of that how much coverage that you will have on the actual code. Strong MBT's models serve as the golden model for computing the test results. Now, this is typical in the hardware industry. The strongest MBT is that models help in generating test cases. Right? MBT often refers to this. So you can model the environment, you can model the support software and hardware, and then you can use the model for actually generating test cases. I think this is one of the contexts in which we get successfully used. For example, model checking, like formula verification technique. We use model checking for generating test cases. Now I will talk about it briefly in the right. I think in this slide. So model-based testing flow, you can talk about design models as one of the inputs, requirements and test specification as another input, and you can have this test generation tool, which is going to generate the test suite, and the test suite can be actually tested against the software code under test, and then you can get the test results. Right? So if you take this test generation tool, you can use a kind of model checker here. So design models are actually, you can take Simulink state flow, you can convert them into abstract, whatever modeling framework, model checking tool that you are going to use. So you can convert them into a set of equations or constraints. If you are going to use some kind of SMT solvers or something, you can convert them for modest size models. You can convert them into a set of constraints, SMT constraints. Your requirements could be converted into some kind of temporal logic formulae. And then you can use, right, if you want to check certain requirements, you actually go and write a property, which is the negation of that property, and then check for, and then use your model checker or SMT solver to check that whether the property is not satisfied or not. Right? If the property is not satisfied, then you are going to generate a counter example. Counter example is essentially giving you a test sequence, and which can be used for testing your software. I think we have used with some success this model checking based technique. So we had used not Z3. What is that Stanford tool? I think we had used it. That was 2 or 3 years before. We took input models as Simulink state flow models and test specifications. We took even coverage specifications as test specifications, and then we generated test sequences which have more coverage, right? And which we compared that with humanly generated test suite, and then we got some results. Of course, one of the challenges in using such techniques is the size of the models that we can create. Another challenge is that some of these design models are so complex, right? And involving pointers and so on. Because you start allowing source code, then you have pointers and complex arithmetics and so on. That poses another challenge. And the third challenge is that requirements, right? So nobody gives requirements. So people write requirements. People have often requirements are in their minds, or requirements are in textual descriptions. So one has to go through that scores and scores of textual specifications and then convert them into formal language, right? That's another. So a lot of manual help is involved before you can go near a verification engine. Right, I think MPT in automotive systems. So as I said, that MathWorks themselves have come up with some model checking technique for generating test cases. In fact, some of the researchers who are working with me, they have joined so MathWorks, and then are authors of these tools. Right, I think we had tried out some elements of these theoretical ideas into practice, and that it is becoming even more practical now. Right, I think many tools exist. Design verifier, I think that is the name of the tool from Simulink Snetflow. So you can look for design verifier. I think this is one of the things which is close to what you have learned in this course. Design verifier allows you to specify properties using some kind of template-based property specification language. You can take your Simulink language, Simulink models, and then you can try to verify them. And of course, you can also generate test cases and so on. Right, 26262 standard and software development. 262 is a functional safety standard defining risk-based integrity levels. Right, some people call it integrity levels like ASIL EA to D to be associated with automotive software components and subsystems. It also defines a product development and verification workflow, right? Something like this. It's very similar to that V diagram. We start with safety requirements, architecture design, software design and implementation. And then on the right-hand side, you have this unit testing, integration testing, and requirement verification. Right, I think your 26262 recommendations is that quite extensive in recommending and mandating different steps. Right, it recommends, for example, formula verification for ASIL C and D. Static analysis of design and code is also being recommended. Functional and structural coverage for ASIL B and D. Right, a lot of coverage requirements, including use of recommending formula verification for very high integrity code, like engine control systems or some of the active safety and advanced driver assist systems. If you look at the kind of testing effort, so I have just given a rough indication of how much time engineers spend on testing at different phases, right? For unit and device testing, days of testing. For subsystem, people use weeks of testing, and really a large amount of time is being spent before people can release their software. Of course, one question is how much of testing is enough, right? This is a 2016 data, so we have new data also. Google car has crossed more than 1.5 million miles of test drive. Even then, now are you confident that you can get into this vehicle, which is supposed to be driverless vehicle, right? Right, of course, testing can only reveal presence of bugs, never their absence, right? Vehicle, yes, any question? Okay. So vehicle level testing is not enough to ensure safety, right? So I think this has been shown by a kind of back of the envelope. To test a failure rate of 10 power 9 minus 9, one has to test at least 1,000 days of 1,000 vehicle fleet for 1 hour each day, right? Multiple such tests are required to debug and revalidate, right? If you find a bug after this, right? Imagine 1,000 days of 1,000 vehicle fleet, right? So this now if you compare it with human driving, 134 million miles per critical crash. No, that's what New York City taxi drivers are supposed to be poor drivers now compared to other poor driving. But still, they have 134 million miles before that. So one has to drive 620 million miles to get 99% confidence. That too, if no critical crash. If there is a critical crash, again you have to go and rerun 620 million miles. Now imagine that no complexity. Right, further challenges. Right, non-deterministic testing arising out of concurrency issues. Machine learning algorithms are being used. No, people want to use them because of their power and expressibility and so on. Testing requires executable systems, relatively late for detecting requirements related bugs. Elaborate infrastructure, I talked about real or model of the plant, high fidelity models. Timing issues, feature interactions, product line testing, right? We are not talking about one software instance, but a whole range of configurations of software options that you need to test. Right? For ESL C and D, even faulty scenarios need to be simulated. People actually inject faults, different kinds of random hardware failures, systematic design failures, and so on. Right? So overcoming the testing challenges, right? I think this is one of the important aspects of that. Right? So you could use some of these techniques, but by all means, none of these techniques are complete enough. Right? And there are individual challenges for taking any of these things and then applying them in reality. Right? Property directed testing, accelerated stress testing, right? First testing, like they use in the security, right? When I talked about this, even security is another aspect. I never talked about it. Now, even functionality itself is a challenge. Safety is another challenge. Security is third challenge, right? A lot of non-functional requirements are also coming in. Right, people are even talking about in the context of AI-based systems explainability. Right, now you would like to explain that why it is doing what it is doing. These are also other testing. Right, so one should probably do correct by construction. Right, can we go and use some of the correct by construction technique? Right, property-based directed testing is a kind of requirement-based testing. Requirements are turned into properties to be satisfied by design or code. Use the properties to generate test sequences which would reveal possible bugs. Right? So we could use some kind of model checking technique. Right? I think this is something, one slide on introduction to this, probably your whole course. Now you must have talked about this at length, and I will not get into this. But the problem is, with this technique is that this is limited to very small size or individual components. Right? I think this is something that we had developed as part of our R&D initiative. Having both combination of model checking for property-based verification as well as for MBT, test case generation. This is something that we had developed at some point of time. So this is also something that we try to experiment with a very, very limited success. Now you start with requirements, create an initial model, and in the context of simulating state flow model, we try to do correct by construction. So start with initial model M1 and then refine them, keep refining them up to some stage, and finally once you are satisfied, you can go and generate code out of that. And the code will be correct by construction. Right? This is a kind of grand scheme that we try to have. Right? In fact, we demonstrated it in a very, very limited context using a using a correct bit construction approach methodology called B methodology, right? So essentially, we took control system requirements, turned them into a kind of model M in B, right? And then that was refined in a series of steps, and then the final model was translated into Simulink state flow. Right? The reason why we did that is that the B model, right? There are two versions of them, classical B and even B, that was used in an industrial context, right? It was not used in the Simulink state flow context or automotive context, but in a kind of controlling the train controllers, automatic train protection system for French railway, right? It is claimed that with 60,000 lines of B, with 10,000 proofs and 22,000 lines of ADA, actually they generated code. And so that the claim is that they had never tested their C code. All the verification was done at the B level, right? So for example, this was repeated later for generating code for automatic train controller in Paris Metro. And also automatic pilot in driverless shuttle at another airport, right? So 187,000 lines of B code, 43,000 proofs were carried out, and 158,000 lines of ADA code. So we were trying to see that whether these successes can be turned into practice in the automotive context. We get very limited success. One of the challenges is that who is going to give these requirements in formal terms, right? Control system requirements are quite complex, many of which are written down in textual descriptions, and some of which are actually implicit. Now, when I have to sit with the engineers, extract those requirements, unless systems are built from scratch, building these requirements are also a big challenge. Now, many of the systems that now we deal with are systems that are already existent, that have been proven in practice and so on. But I think this is another thing which could hold some promise. Accelerated stress testing, robustness testing that tries to stress or fail the system, right? This is something like in the security, people talk about first testing. Large number of possible failure scenarios are simulated. It is contrasted with slow, regular road testing. We could also do runtime safety monitoring. I think this is also being attempted. In fact, one of the recommendations from 26262 is to have runtime safety monitoring. So build an independent system that looks for possibility of unsafe states in the system and bring the system to safe states. Now, these systems actually focus on safety. They do not implement full functionality, right? By not implementing full functionality but focusing only on safety, they can be very simple. They're very deterministic, so they are less error prone, right? Because otherwise, who is going to prove the prover themselves? Verification problem is that who is going to check or verify the verification systems itself? Now, there is an infinite regress that is involved. So the verification system needs to be simple enough so that it is beyond doubt that the verification system is error-free. So in this runtime safety monitoring, if you're doing only safety checks, not doing full functionality, then they can be simple, they can be deterministic, and easy to verify rigorously using formal verification technique or extensive testing. So I think this is also one promising approach, right? So essentially, accelerated stress testing, runtime safety monitoring are some of the things one could employ. So I believe there are two pillars for doing kind of more rigorous verification and validation. Right, one is formal requirements engineering. Right, so we need to have next generation requirements engineering that supports formal and precise specification. Of course, it should start from school, right from school. So people need to be taught formal and precise, how to write formal and precise specifications. Right, I think writing specifications is one important step or activity that are often ignored. People directly jump into code, right? It's a question of what versus how. Now people should be taught to develop, think about what rather than how. And then of course high level model engineering, right? Next generation modeling that supports extensive modeling including physical control systems, implementation platform, and environment, and also in a kind of stepwise refinement fashion, now from abstract and high level modeling to low level modeling, right? In contrast to modeling that is directed towards implementation. And I think with this, probably I will conclude. So I think this is something that I have already talked about. I think I will keep this slide and then maybe wait for some questions. Now, if you have any questions, feel free to write on the chat box or you can ask me. Thank you.
Sir, there is a question from Mr. Pushkar Kishore. He wants to ask why LiDAR is being withdrawn by many companies.
Why LiDAR is being
withdrawn by many companies?
Right. I think that's a well-known problem. I think to have LiDAR or not LiDAR. So LiDAR brings in its own complexity, right? One of the major thing is that so you need to go and install it somewhere, right? And miles and miles of running, right? There are some issues related to its installation and working, and then what is the added? What is the trade-off for that, right? For the efforts that you are going to do with LiDAR, what is the trade-off that you are going to get because of some of the recent successes with Tesla, right? Tesla is one thing, which always uses camera-based sensing, and which claims that camera-based sensing should be good enough. Camera with LiDAR, right? That is one of the reasons. Looking at the successes of Tesla, people are also trying to mimic that. And of course, LiDAR installations and then LiDAR data processing and so on, they have their own challenges. But still, there are some industries, some OEMs, who believe the role of LiDARs in a strong way.
Sir, he has another question. What is the accuracy of the AS when the detected object is static?
What is the accuracy of what?
Of the AS.
What is AS?
Oh, I don't know. He has written AS.
Oh, autonomous system. Okay,
Maybe.
so autonomous driving, right? So I think it is difficult to predict because the sensors are becoming this is a whole evolutionary thing, right? Now it is evolving, and so when you talk about detection, right? There are many elements that are involved. One is the kind of raw sensor inputs that are coming in, and then you need to do processing of those, and then identify them as an obstacle, right? So of course, static objects are better than, and also the kind of objects that you are talking about, right? People can very easily recognize large objects like signaling stands, trees, buildings, and so on. But if you talk about, and also when you talk about detections, there's a kind of whole range of things, like what kind of lighting conditions that you're talking about, whether there are any shadows or not, what is the angle of the, where the objects are situated and so on, right? And it's highly evolving, right? I think it's difficult to answer this with a kind of single answer.
Okay, sir. So thank you, sir. So, sir, I have a question that whether these autonomous systems are mixed criticality systems.
What criticality systems? I didn't catch the first word.
Mixed criticality systems.
Um, Mixed criticality is used in a kind of okay, so it's in a kind of real-time systems
Yes, sir.
context you are using. Right, that's right. I think it's a mixed. See, there are some elements, there are some components, subsystems like engine control systems or now your electric motor control systems. They are highly embedded real-time control systems, time triggered and mixed criticality.
Yes, sir.
There are some elements like body control and so on. They are discrete control. So
Yes, sir.
you can think of them as mixed mixed criticality systems.
And sir, this ISO 26262 is also have that uh, the different levels that you have mentioned, that from A to D.
Right, that's correct. That's correct.
So that is also comes under mixed criticality system, I guess.
Right. I think see, D is the kind of highest level of criticality.
Yes,
So
sir.
this is coming from the kind of failures. How much of failure is uh, tolerable, right, for the given applications and so on. So if you take D, then that is the highly critical one. Okay, so
Yes, sir.
safety critical one. Okay,
Uh,
so there you need to have extensive validation. You need to have detection mechanisms need to be built in. Now, any faults are there, you need to build in detection mechanism and then recovery mechanisms and so on.
sir,
Okay.
so in these autonomous systems, you must have used some scheduling algorithms for means any type of scheduling algorithm you have used in this autonomous system.
Yes. So when you talk about autonomous systems or even traditional engine control systems, there are standard scheduling algorithms used. Most of them uses static scheduling algorithms, right? And then the AutoSAR architecture that I was talking about, they don't allow static dynamic creation of tasks and so on also, right? So any element of dynamism is carefully looked at. If it is a low criticality one, like ASLA and so on,
Yes,
for
sir.
infotainment systems and so on, you can use dynamic scheduling algorithms. But for high criticality like ASLD and so on, you do use only static scheduling. In fact, there may not be any scheduling also. It might be a kind of sequential piece of code. At the level of design, you think of them as concurrent pods, but you go and statically schedule them.
Okay, sir. Thank you, sir. Thank you. Thank you for the clarity. So, participants, if you have any question, you may ask, sir. So, sir, I think there is no more questions from the participants.
Okay, good. Thank you very much.
So, sir, I
Hope
want
that
to.
participants got something out of these 2 days of lectures. So thanks for giving this opportunity and best wishes to the participants.
So, sir, thank you very much for this informative and elaborated talk. I hope this lecture will enlighten the participants as well as the faculty members of different universities who are present here in this virtual meet to choose cyber physical system as a research field. So we also hope to host you at NIT Jalandhar in near future if you permit. So, and finally, I want to sincerely thank you for spending your valuable time and effort for us. Thank you very much.
Thank you. Thanks for all the support. Best wishes. Have a great evening.
Thank you, sir. Thank you.
Thank you.
Okay, dear participants, feedback link will be available within 5 minutes, and just wait for that in chat box only. Okay, and there is a slight change in the tomorrow's lecture timing. I think it will be on 11 a.m. and the speaker of that one is Professor Virendra Singh sir. Okay, so initially it was 10:30. Now there is a slight change and it will be at 11 a.m. Okay, so just wait for 5 minutes and link will be available in your chat box. Okay, thank you.